EU Regional School, today here with our guest from ETH Zurich, Professor Andreas Fichtner. So just a bit of an outline. This EU Regional Schools, as all of you know, maybe most of you know, is a format which started already with the beginning of the graduate school ACES. So we always had the idea back then to invite researchers who are experts in their field to give us a bit of an overview in the fundamentals and the basics of a topic that is related to our research, and a bit of an outlook into the current state and the maybe in the future of some exciting topics. So in this course we had many interesting talks and presentations, and today it's a really big pleasure for us to have Andreas Fichtner here as an expert on inverse problems and full waveform inversion from ETH Zurich. So just a quick introduction to the work of Andreas and where he's coming from. So he actually did his undergrad in Freiberg at the Bergakademie Freiberg in geophysics, and then after a stay in Washington did most of his education, so master's and especially also his PhD at the LMU in Munich, in the also very well-known research group on seismology. After that, he was a postdoc researcher in Utrecht, and since 2013 already, he's a professor at ETH Zurich. Since 2018, also as associate professor. As I said, I mean, a lot of the work of Andreas is related around full waveform inversion and inverse problems. But if you look through his research track record, you can see also a lot of interesting aspects in more fundamental aspects of inverse theory, which is also, I guess, of a lot of interest to many of the students here, and applications in diverse areas. Andreas received a quite wide range of awards in the meantime. Maybe really important is this very early already a Fulbright scholarship for this stay in Washington, I presume, and several prizes for papers and presentations. Also really remarkable is, of course, a starting grant in 2016, ERC starting grant from the EU, one of the very high grants that you can get as a young researcher. And and the moment also in the Bavarian Academy of Sciences. That's also, of course, an important achievement. Okay, so today he will talk about full waveform inversion in and inverse problems in geophysics in general, I suppose. As I said, we have this as a bit of a lecture format. So typically we have two blocks of 1.5 hours. We are a bit flexible in terms of the timing, so we leave this to Andreas to see how this fits best. I will leave it to you, Andreas, maybe to say how you would like to have it organized in terms of questions and so on.
Yeah, I mean, yeah, first of all, many thanks for the nice introduction and for the opportunity to speak here. It's really nice to see so many young and so many new faces, and I really very much hope to see many of you in person in not too far future. Concerning the format, yeah, I think it should be pretty relaxed. If you have questions in between, please feel free to ask them. If this is just something that is short for the basic understanding and something I can answer quickly, I will certainly do this during the lecture. If this is something that needs more discussion, we'll probably keep this for the break. And good. So I will start sharing my screen. Okay. So can you all see this in full screen?
Yep.
Yeah, perfect. So first of all, I of course would like to mention that the work that I will present is not just myself. I have a few really brilliant PhD students and postdocs, most notably Lars Gebrat, who will actually give part of this lecture. He knows many, but in particular one thing a lot better than I do. So I will leave that part of the lecture completely to him. That will be a little bit later. But also Dirk Philipp van Herwaarden, Andrea Zunino, Sylvie Trasterson, Christian Böhm, Martin van Driel, and quite a few others. So it's really collaborative work accumulated over quite a few years. So as Florian mentioned, I'm basically a seismologist, and where I'm coming from is solving inverse problems that help us to constrain the internal structure of the Earth, mostly using earthquake data. So I thought before I really go into more detail, I give you a little bit of an introduction to this so that we are all on the same page. So the first few slides will be about constraining Earth structure using earthquake data. And I want to start this with a little movie. What you see here is a numerical simulation, a spectral element simulation of the Great Tohoku earthquake that occurred on March 11, 2011. It had a magnitude 9.1. It was the fourth largest earthquake ever recorded, and it liberated literally within a few seconds the unbelievable energy of 3.9 times 10 to the 22 joule. Nobody has any understanding for that, but I can tell you that this is about 77 times the world energy consumption. So everything from a light bulb to a big industrial installation, everything together, a whole year, the whole Earth is actually 77 times less than the energy liberated by that earthquake. So it was massive. And it was so massive that, of course, it was very easily recorded by seismometers all over the Earth, and in particular in the Black Forest Observatory, which is actually pretty close to Zurich and also not too far from Aachen. The Black Forest Observatory, it was at an epicentral distance of 83.3 degrees from the earthquake, so roughly a quarter around the Earth. And there one could record the ground motion that you see on this slide. So what you see are displacement seismograms. The vertical axis, let me see if I can paint here. Yeah, the vertical axis that you see here, it's 0.01 millimeter per second. So because of the large distance, the displacement was actually relatively small. And you see that roughly those seismograms in vertical direction on top, east-west in the middle, and north-south direction on the bottom, essentially falls into two parts. There's this first part that contains wave arrivals that have a pretty small amplitude, like this wave here. This is actually a P wave. It's a compressional wave that arrived after about 747 seconds. And there are many others throughout this part, and these are the body waves. So these are waves that literally propagate through the interior of the Earth. So if you imagine the earthquake, for example, here, a receiver there, then those body waves, they literally travel through the center, through the interior of the Earth. The second part are those surface waves. Those surface waves, they have a much bigger amplitude. And the reason why they have a much bigger amplitude is that they're actually not traveling through the interior of the Earth, but they're traveling across its surface. And since they're only spreading their energy in 2 dimensions and not in 3 dimensions, they have a larger amplitude. So these are the recordings that we are trying to use in order to constrain the internal structure of the Earth. So we're basically trying to use aspects, for example, the travel times or the amplitudes of those body waves, those surface waves, in order to constrain structure inside the Earth. Now, a few words about the nature of this inverse problem. Well, obviously, as I already mentioned, the sources that we're using, the energy sources that we're using, are earthquakes. And earthquakes, by their very nature, are quite poorly distributed. And this is what you see in the figure to the left. This is a collection of about 22,000 earthquakes that have been located by the United States Geological Survey in 1998. And you see that all of the dots that represent an earthquake are very heterogeneously distributed, mostly along the boundaries of tectonic plates. For example, along the boundary of the Pacific plate, which you see here. Right? But there's very little earthquakes inside those plates. Also, those sources, those earthquakes, they like to reoccur in almost the same places. And they have a quite remarkable bandwidth, roughly from 5 Hertz to 0.5 millihertz. So these are roughly 13 octaves. So these are really broadband signals that we're dealing with. And of course, ideally, we would like to use this whole bandwidth, but admittedly, we are quite far away from that. Also, in contrast to what people do, for example, in medical imaging, the position, the timing, and the mechanism of those sources is a priori actually not known. So that means the inverse problem that we're solving is inherently a coupled problem, where we try to constrain both the structure of the Earth, but also the distribution of the sources. Our receivers are called seismometers. There are many different forms of seismometers, but that's not so important here. But they are also very poorly distributed. And some typical source receiver configuration is actually shown here to the left. This is from a seismic tomography that we performed in our own group. And you see that all the black triangles are receivers. These are all seismometers. And you see that they suspiciously cluster into economically powerful countries, but less so in countries that are economically less powerful. There are also hardly any seismometers in the vicinity of the poles, and of course not in the oceans, at least very few. So they're also very heterogeneously distributed, which also sets seismic tomography or seismic imaging in this context apart from what is done, for example, in medical imaging or non-destructive testing. Those seismometers have variable characteristics. They have different bandwidths. They suffer from different side effects. But mostly, we are lucky. The recording bandwidth actually often covers the observable bandwidth. Currently, about 10,000, order of magnitude 10,000 of those seismometers or recordings from those seismometers are openly and freely accessible. The medium that we are trying to image using those sources and receivers is the Earth. And the Earth is viscoelastic and it's anisotropic. Furthermore, the Earth, at least when you're looking at a global scale, it's actually rotating, as we all know, and it's also self-gravitating, which means that when you deform the Earth, it actually tries to restore its original form, not only because it is an elastic body, but also because it has gravitation. And that gravitation basically tries to pull it back into a roughly spherical shape. Also, the Earth has topography, not only external topography, but also topography on internal discontinuities. It has oceans that are fluid, and also an outer core that is fluid. So it means it's a solid fluid medium. Of course, these are lots of complexities, but as always in physics, you need to simplify. And the complexity that you actually need depends very much on what you want to find out about the Earth, but it also depends on the complexity and the amount and type of data that you're using. Does your data actually require that complexity in order to be explained reasonably well, or does it not? And of course, this has to be considered on a case-by-case basis. Since the Earth is viscoelastic and anisotropic, it can be fully described only by a very large number of parameters, order of magnitude 30. So if you really count how many unknowns do you have in the Earth, you come to about 30. But most frequently, we only try to resolve a subset of those, namely a subset to which our data are actually sensitive. And mostly, in the large majority of cases, at least in global or regional scale seismology, these are the travel times or the velocities of P waves, of SH waves, these are horizontally polarized waves, and of SB waves, these are S waves, shear waves, with the vertical polarization. And here you see we have different wave speeds for SH and SV, meaning that those wave speeds actually depend on polarization, which means the Earth is anisotropic. Now, during the past decade, or I would say almost 2 decades, we have seen a transition from traditional travel time tomography, it is symbolized here to the left, where we use the arrival times of a discrete number of waves, for example, of a P wave, of a later arriving S wave, and so on and so forth. This is very elegant, and it's computationally very fast, but it does not use a lot of information. Much of the information is thrown away. And that's why we have seen this transition to what we somewhat optimistically call full waveform inversion. We don't use full waveforms, for sure not the whole bandwidth, and also not every single wiggle. It more represents a dream, I would say, of literally using every single wiggle in a seismic, so the complete recordings. This is intended to, of course, first of all, exploit more information, or as much information as is possible, for example, on the basis of our computational resources. And this in order to improve tomographic resolution, to see more detail inside the Earth, to correctly account for wave propagation physics inside the 3D complex Earth, that would allow us to avoid forward modeling artifacts, but also to correctly account for finite frequency sensitivity and nonlinearity in our inverse problem. And there's the hope that this would allow us to avoid inverse modeling artifacts. And so full waveform inversion in this ideal is intended to improve our tomographic imaging on really different levels, on different fronts. Now, there's broader relevance to this full waveform inversion. So in principle, I will give you a talk about seismology, but I want to tell you that that this is not only interesting when you're a seismologist, but it really has relevance that goes beyond that, simply because math and physics are so transportable between domains, and because wave propagation occurs not only in seismology, but in many other branches of sciences as well. So in addition to studying dynamics, evolution, and composition of the Earth, the seismic tomography, or this full waveform inversion, can be used, for example, to study the internal structure of the sun at a completely different spatial scale. Also, those full waveform inversion models that you produce, they are very useful in earthquake source inversion, so learning about the properties of earthquakes. They're essential for reliable tsunami warnings, but also for the monitoring of the Comprehensive Nuclear Test Ban Treaty. This full waveform inversion that we will see here mostly in seismology can be translated to much smaller scales, to exploration and reservoir monitoring, to engineering applications, for example, tunnel building or building of dams, of reservoirs. But also there's lots of technology transfer between full waveform inversion in seismology and medical imaging and non-destructive testing. And in fact, what you see here to the right is a mixed image. To the left, you actually see a full waveform inversion of a human breast. The blue thing that you see here in the middle is actually a breast cancer. And to the right, you see shear velocity inside the Earth plotted at 100 kilometer depth. And the scaling between the two in time and in space is about 10 million. But apart from that, the math and the physics are very similar. So there's more relevance to what I will talk about. So we have about 11 orders of magnitude in spatial scale. A few words about the challenges and motivation for this talk and for the research that I will present. I think everybody knows that over time we have faster and faster supercomputers. And this is combined with improved numerical methods to solve all sorts of equations, partial differential equations, for example, the wave equation or different wave equations. And that allows us to do many different things. For example, to properly account for, so previously mentioned, wave propagation through complex three-dimensional Earth models, but also for the nonlinear dependence of the observations that we're making, the waves that we see, and the model parameters that we're interested in, like velocities, attenuation, or others. Now, this in turn enables this full waveform inversion, or those full waveform inversion methods. As I said, we don't use full waveforms yet, but we're getting there. It's a progression, and those full waveform inversion methods, they have shown to provide structural models with really unprecedented resolution, with unprecedented level of detail, and that has significant impact for research in seismic imaging, in medical ultrasound, non-destructive testing, but also other domains. So this is all nice and good, but there are some problems here. And the first sort of curious one is that even though we obtain tomographic images that visually contain a lot more detail, actually our ability to quantify the uncertainty in that incredible level of detail that we recover has actually been reduced, simply because the methods that we are applying today are computationally so expensive and so involved that actually uncertainty quantification becomes a lot more difficult than it used to be, for example, within this beautiful machinery for linear inverse problems. And so if you solve linear inverse problems, everything is pretty, it's very elegant. It's clear how to do uncertainty quantification and resolution analysis. But all of this falls apart when you try to do full waveform inversion, where suddenly you're dealing with a nonlinear problem that may have many different solutions that are actually not very close to each other. The consequence of this is that we have more and more difficulty to actually find alternative models that explain our data equally well. We know, or at least we suspect, that there are models that are significantly different from a particular one that we retrieve, but we don't really have efficient mechanisms to actually find alternative models and then to see how different are they actually. Right? Are they very different, meaning that we are very uncertain in what we are able to see? or are they actually in any case close to each other, which would mean that what we infer is actually quite certain. And another consequence is that, of course, we have actually more difficulty to interpret tomographic images from full waveform inversion with the high confidence that we would actually like. And so, for example, the doctor who sees this apparent image of a breast cancer, that person would like to know how certain is that actually. But quantifying this has become very difficult. So based on this lecture has a few very simple goals. The first one is to present a collection of methods that enable 3D probabilistic full waveform inversion with complete uncertainty quantification. This is not to say that we are there at the moment, right? But I think these are some methods that put us on the right path. And those methods roughly fall into two classes. The first one is intelligent Monte Carlo samplers. And the second one is methods that help us to accelerate forward and adjoint simulations of seismic wave fields or other wave fields. A brief outline, what I will talk about. The first one is about Hamiltonian null space shuttles. And those Hamiltonian null space shuttles, they're basically artificial Hamiltonian systems that allow us to produce alternative models, alternative in the sense that they also explain our observations. And it does that in a computationally very efficient way, and also in a, I find, physically quite insightful way. Based on this, I will go the next step to Hamiltonian Monte Carlo, which is very closely related to Hamiltonian null space shuttles. It's basically a probabilistic version of it. And this already allows us to do probabilistic full waveform inversion, not in 3D yet, but in 2D, and actually with computational resources that allow you to run this on a laptop, which I find is quite remarkable. Now, this Hamiltonian Monte Carlo, as all Monte Carlo methods, requires tuning, and Hamiltonian Monte Carlo needs a lot of this. And so it's desirable to devise methods that allow Hamiltonian Monte Carlo or other Monte Carlo methods to actually tune themselves on the fly. And this is what I will present in the third chapter. It's a method where by Hamiltonian Monte Carlo or also other Monte Carlo methods can essentially find the optimal tuning while they're running. The fourth chapter is a bit different from this. It's about a method that we call smoothie SEM. It is a spectral element method for the simulation of wave propagation that allows us to accelerate this by using meshes, finite element meshes that are adapted to our prior knowledge on the geometry of the wave field. So it falls into the category of accelerating forward and adjoint simulations. Then the fifth chapter, which is actually the one that will be presented by Lars, is on reusing information that we acquire in the course of this Monte Carlo sampling. And it does that using physics-informed neural networks. And then finally, I will give you an outlook and give you an idea of how close or how far we actually are from this ideal of running 3D probabilistic full waveform. Good, this was a long introduction, but I hope we are more or less on the same page, and that was the idea of that. Before I actually jump into the actual meat, a few notes on style. I think just as also you are pretty tired of virtual lectures. I think you have seen too many of those. And as a consequence, I will not bombard you with hardcore mathematics. So this presentation, it will be rather colorful and casual. So the focus is really on concepts and not so much on rigorous math. You will see very little math. And so my goal is really to whet your appetite and to get you interested. At the end of the presentation, you'll see a collection of publications. If you want to know the mathematical details, you're invited to look at them. And if you have any more questions, then of course, feel free to contact me. So the first chapter, as I said, will be on Hamiltonian null space shuttles. And so here's what this is. We start with a little bit of preparation and a problem statement. So first, let's talk about what the null space is, or the effective null space. The effective null space is not the exact mathematical null space. It's a different thing. There's no very clear definition, but still I'll give it a shot. We start off with some misfit functional chi, and that misfit functional depends on a model. or on a parameter vector. So that could, for example, be some tomographic model of the Earth, of the human breast, or of something else. And that misfit functional quantifies how well the synthetic data that we compute on the basis of M actually explain our observations. Now we make a big step and say we have some algorithm, and on the basis of that algorithm we find some model M hat that we actually find acceptable. So this is one of certainly infinitely many models that explains our observations to within the uncertainties, roughly. So what we are interested in is a collection of models that also explain our observations to within a certain misfit tolerance. And that misfit tolerance is what we call epsilon. And we will call all of those models M hat plus delta M that actually explain our observations to within that tolerance as the effective null space. So if you draw a model from the effective null space, M hat plus delta M, the misfit that this modified model, this alternative model produces, will be smaller or equal than the misfit of the model that we found before, that we already found acceptable, plus some tolerance that we may choose subjectively. Okay, so the problem is, how do we actually find models that lie within the effective null space? And we know we defined what the effective null space is, but how do we actually get there? How do we find this M hat plus delta M such that that misfit actually remains acceptable? Why is this relevant? Well, of course, as I said in the motivation already, it's relevant for uncertainty analysis. We want to know, are there alternative models that are very different from that acceptable model that we found before? And also, we may actually want to use this the other way around. But just imagine you found a model that you like, and you want to modify this model. So you want to sneak in a certain feature into that model, and you want to do it in a way such that the misfit actually remains acceptable. And you may think of this as an informed way of hypothesis testing. Like modify a model in a certain way, for example, in reservoir geophysics, maybe sneak in a gas reservoir in some corner of your model. And you want to know, when I sneak in this gas reservoir in my model, does it still explain my observations or does it not? Right? Or you may see a gas reservoir in your model and you may want to get rid of it. Right? So if you erase that gas reservoir that your algorithm has imaged, do you still explain your observations or not? Right? If you do, it may actually not be there. So this is the relevance of this. So there's a trick, and here's how this goes. It has two parts, but one of the trick is we take this model M, and we interpret it as the position of a particle in a very high dimension. So just imagine our model space may have dimension 1000. So we have 1000 free model parameters. And instead of considering this as, say, a model of the Earth or the human breast or some other thing, we consider this as the 1000 dimensional position vector of some imaginary particle. And so it's an artificial position vector, it's just a reinterpretation of it. And then we assign to this position vector M a potential energy. And we simply say that potential energy, U, depending on this position or on this model, we just set this equal to the misfit of that model. It's a definition. It's arbitrary at this point. But you will see later which purpose it serves. And then now we have assigned a potential energy. Let's go a little bit further and let's invent more things. So we can also actually assign it an artificial momentum. We just dream up some vector. P has the same dimension as the model vector M. And now that we have P, we can as well define the kinetic energy. Right? So the kinetic energy of that momentum vector that we have just invented, this is equal to 1/2 P transposed M to the -1 times P. And this M that you have here, it's a so-called mass matrix. Right, so now we invented lots of things. We invented a kinetic energy, a potential energy, that's the misfit. We just came up with some artificial momentum. Nobody knows right now where this is coming from, but let's just invent a vector. Based on this vector, we define the kinetic energy, 1/2 p transposed m to the -1 p, and m is a mass matrix. And all that mass matrix has to do, it has to be positive definite. But apart from that, that mass matrix is something we can choose free. So now what do we have? This kinetic energy at this point is totally undefined. But what we now do is we actually say that for some initial momentum that we give to this high dimensional particle, the initial momentum is p hat. We say that the kinetic energy corresponding to this initial momentum is equal to our misfit tolerance that we had before. So this epsilon is the misfit increase that we're just about willing to accept. And we say that the initial kinetic energy of our high dimensional particle is equal to that tolerance. You'll see why that is useful. Now we have kinetic energy and potential energy. The sum of these is the total energy, and this is also called the Hamiltonian in classical mechanics. Okay, so now comes part 2 of the trick. Now we have this particle. We have given it some initial momentum and some initial kinetic energy, and it has a potential energy. And now what we can do is we can actually let that particle fly along a certain trajectory. So essentially what we did, we had a particle that is sitting somewhere, and we're kicking this particle. We give it some momentum, so it starts flying through this high dimensional space. And the trajectory along which it's flying is determined by Hamilton's equations from classical mechanics. And Hamilton's equations are written here. So the time derivative of the model parameter is equal to the momentum derivative of the Hamiltonian, and the time derivative of the momentum is the negative derivative of the Hamiltonian with respect to our model parameters. Now, the thing is, h, so the total energy in classical mechanics, is actually constant along a trajectory. You can literally imagine this as a high-dimensional planet orbiting around some high-dimensional sun. As the planet is orbiting, it conserves its total energy. So what does that mean? So it means that total energy h here, which depends on the model parameter or the position as a function of time, and the momentum as a function of time, this total energy is equal to the misfit chi for a certain model or position at time t. Right? This is the potential energy, which we define to be equal to the misfit, plus the kinetic energy, which we defined as 1/2 times the momentum as a function of t transposed m to the -1, and again times the momentum as a function of t. And that quantity h, the total energy, is preserved as that high-dimensional imaginary model flies through this high-dimensional space. Now, what that means is here that the total energy h at some time t is equal to the initial total energy. And that initial total energy we have actually seen before. That initial total energy, this is equal to the potential energy at time 0, which is just the misfit at the model that we found acceptable at the beginning, plus the kinetic energy at the beginning of the trajectory. Right? So, and we said that initial kinetic energy, this is actually equal to the tolerance that we're willing to accept. So this is our misfit tolerance that we may choose, for example, on the basis of our observational errors about which we have statistics. You know, may come from somewhere else. Now let's kick out a few terms here. What do we have? We have the misfit for some model after time t, plus the kinetic energy at time t. And that kinetic energy, because we require the mass matrix to be positive definite, this kinetic energy is strictly positive. That's a positive quantity, a proper kinetic energy. Then we have the original misfit at the model that we liked, chi of m hat, plus this kinetic energy, which we already said is equal to the tolerance. And then if you stare at this a little bit longer, you realize that since the kinetic energy is a positive quantity, we actually find that the misfit chi for any model along that trajectory is smaller or equal than the initial misfit for the model that we found acceptable at the beginning, plus our tolerance. But that means that all the models that we find as we fly along this trajectory are indeed inside the effective null space. So this is the recipe here. You invent a Hamiltonian system. You interpret your model as a particle that's sitting somewhere. You kick that particle, it starts flying, and it flies along a trajectory. And at each point of that trajectory, it produces an alternative model. And by construction, the misfit of that model that you produce along that trajectory will be acceptable. It will be smaller than the initial misfit plus some tolerance. So that was the basic concept. Now there are many variations of the theme. So depending on various choices that you can make, subjective choices, or informed subjective choices, the shuttle actually behaves in different ways. You may, for example, say that the tolerance that you allow is 0. So you see, you found a model that you like, and then you say, okay, all other models that I find must have a misfit that is smaller than that acceptable model that I found in the first place. And then actually you can show through a few manipulations that in this case, the null space shuttle, as I have just introduced it, actually becomes exactly equivalent to gradient descent methods. Right? So instead of allowing also for models that have slightly higher misfit, your null space shuttle always flies towards models that have lower misfit. And you can actually show that this is the same as gradient descent. And the specific method, the specific descent method, depends on the choice of the mass matrix. So for example, if you choose the mass matrix to be unit matrix, then the null space shuttle actually becomes the steepest descent method. If you choose the mass matrix to be the Hessian of your misfit, then it becomes Newton's method. Right? So it's actually a special case of the null space shuttle are gradient descent methods. You can also actually prescribe a takeoff direction. So far, we considered kicking the shuttle in some direction, but you can actually kick it in an informed direction. And the direction into which you kick the shuttle controls the features that you're trying to add. So I mentioned this gas reservoir example. Right? So the direction in which you kick your shuttle may actually be the direction of a gas reservoir. We will see an example. And also you can, based on the choice of your mass matrix, ask your shuttle to find your alternative models that are rougher or smoother than the model that you found in the first place. Of course, finding rough models is easy, but finding alternative smooth models can actually be quite interesting. So here's an example. The example is a nonlinear travel time tomography, just in 2 dimensions, because it's fast to compute. The model domain that we're looking at is 40 kilometers in y direction or in vertical direction, and 80 kilometers in horizontal direction. The sources are at the bottom, with just a few, and all the receivers are close to the servers. And the model that you see here, so this is a velocity model in kilometers per second, this is the color scale. This is actually a model that explains the observations to within the uncertainties, to within the observational uncertainties. And now we want to modify that model and see if we can find alternatives. And so we give our particle, we interpret this model that we see here as a high-dimensional particle, and we give it an initial momentum. And that initial momentum, p hat, has the form of a Gaussian block. So that Gaussian block may be the shape of the gas reservoir that you want to sneak into that tomographic image. And then we let the shuttle fly. And indeed, what you see after 4 seconds, after 4 invented seconds, it's not a real physical quantity, the Hamiltonian system is made up. But after 4 seconds, you indeed see this gas reservoir or whatever popping up in this model. And the model that you see here on the right actually has a misfit that is acceptable. Right? It's within the observational uncertainties. And you see this quantitatively in the figure below. In blue, you see the total energy, which is here at the beginning for this model. This is the total energy. And it remains constant by construction as you fly along that Hamiltonian trajectory. Below here, you see the kinetic energy. This here, this height, this is epsilon. Right? So this is the kinetic energy that we give to our particle. And then the initial potential energy, so the initial misfit is down here. And then as the shuttle or the model starts flying, the potential energy increases, or the misfit increases, because you give it momentum. Right? And it evolves towards other models. But the total misfit, the misfit always remains below the total energy. It always remains by construction below that barrier. So you then, after longer time, after 24 seconds, imaginary seconds, you see that you come up with, again, a different model that also works well. So this is the model that would be here. And after 48 seconds, you come up with a model that again looks different and would be here. And all of those models explain the observations to within the uncertainties. This can, of course, be cast into a movie. That's what you see here. So every single model, every time snapshot that you see here is an alternative model that explains the observations. Right? Note that you produce alternative models without Monte Carlo sampling, just by solving Hamilton's equations, which is just an ordinary differential equation. Instead of adding this Gaussian blob, you may also add random perturbations. This is what you see here. And depending on which kind of momentum you add, you retrieve different alternative models. So you can really mass produce alternative models, either randomly or in an informed fashion, for example, through hypothesis testing. So some preliminary conclusions. I will have conclusions at the end of each chapter, also to give us a small mental break after each chapter. So what we have seen is that we have a method for efficient null space exploration for nonlinear inverse problems. But note that there was no point where I required the equations to be linear. And does this without Monte Carlo sampling. The whole thing rests on the construction of an artificial Hamiltonian system. The data misfit produced by some model is called the potential energy. And the misfit tolerance that we can accept is essentially the kinetic energy. And basically potential and kinetic energy together allow us to evolve this Hamiltonian system in time through the solution of Hamilton's equations. This null space shuttle is, as I've said, I haven't proven this mathematically, but this will be in one of the papers that I show in the end. It's actually a hybrid between gradient descent and Monte Carlo methods. When the tolerance is 0, it becomes a gradient descent method. And the specific type of method depends on the mass matrix that you choose. And if you draw the momenta repeatedly in a random fashion, it actually becomes Hamiltonian Monte Carlo. And this Hamiltonian Monte Carlo method is what I will talk about in the next chapter. This null space shuttle can be used for different purposes. For example, for quantitative hypothesis testing, for the targeted construction of alternative models with specific features that you want to sneak in or that you want to get rid of. And you can use it, for example, to construct alternative models that are rougher or smoother. And of course, there may be many other ways of using this null space shuttle. Okay, so this brings me to the next chapter, which is on Hamiltonian Monte Carlo. For those who haven't been there, what you see in the background is actually the famous casino in Monte Carlo. So I couldn't resist to put that in. Good. So again, a little bit motivation in addition to the motivation that we had before. It may be a bit simplistic for some of you, but still, I thought it's worth adding. So Hamiltonian Monte Carlo actually has been introduced quite some time ago under the name hybrid Monte Carlo in quantum mechanics, already in 1987. It took a surprisingly long time before it sneaked into geophysics. Almost 30 years. Very remarkable that such an effective method can hide from geophysics for such a long time. Says something about our community. Maybe our community is just small so that we are less efficient in actually discovering things. It's a random walk method that can be used to sample a probability density, any probability density. But of course, here we're interested in a specific one, namely in the posterior probability density of an inverse problem. And the whole algorithm is actually motivated by a very well-known deficiency of the Metropolis-Hastings algorithm that in fact already Nicholas Metropolis discovered when he came up with that method many, many decades ago, in the 40s. And this is illustrated here. Our goal is here, very simplistically, to sample a two-dimensional probability density that you can see here. It's a toy example, but it's still good for illustration. And essentially, you have two choices. The first choice is you go in baby steps. You do very small steps as you traverse model space. So you may start off somewhere. And in each step, you advance a little bit in model space. Now, this has the advantage that when you only make small steps, that the next model that you find is very likely to be accepted. Because you're not going far from a model that is reasonable. The next model that is very close is pretty likely to be reasonable as well. Right? So it has the advantage of a high acceptance rate. Many of the models that you produce will actually be accepted, but of course it has the downside. So the plus is high acceptance rate. The downside would be very slow model space exploration. You're going in baby steps. It takes ages before you actually make your way through model space. The other extreme would be going bigger steps. Now, of course, by construction, you traverse model space a lot faster. But the disadvantage is that if you go a big step away from a model that is reasonable, the likelihood that the new model is actually reasonable as well and will be accepted is very low. And the likelihood that it is reasonable decreases phenomenally fast with increasing model space dimension. Right, so, and high model space dimension is already a dimension of 10. So actually not high. And so the plus would be you explore model space very fast, but your acceptance rate can be so ridiculously low that the method actually becomes useless. And that happens very quickly, as I said. It can happen when your model space dimension is 10. So not very interesting for many problems. So Hamiltonian Monte Carlo is designed to repair those problems. And it does so by taking advantage of derivative information. And this taking advantage of derivative information allows it to actually combine the two apparently discrepant things, namely making long distance moves and having a high acceptance rate. So you get both. And the price to pay is you have to provide derivative information. And this turns out allows it to solve relatively high dimensional problems that we are interested in many geophysical or engineering or medical applications. A conceptual introduction. So you have in principle already seen this. So what we do is very similar to the null space shuttle. So we start with some initial model. We actually called that M hat in the null space shuttle chapter. But let's assume here that this has been drawn randomly. And then we say that the potential energy of that model, which we again interpret as a high dimensional particle, is the misfit, and we call this again U. So then we may indeed interpret this just for our brains as a shuttle, as a particle that is sitting somewhere, and say it's orbiting around some maximum likelihood model. Then we draw a random momentum. So we basically kick that shuttle in a random direction. Here, in the context of Hamiltonian Monte Carlo, this is a purely auxiliary quantity. That random momentum that we draw defines a kinetic energy that we again call K. And then we solve again Hamilton's equations. So we have a potential energy, we have a kinetic energy. The sum of the two is the total energy, or the Hamiltonian. And once we have the Hamiltonian as a function of m and of p, we can solve Hamilton's equations. And Hamilton's equations basically let that particle, or the shuttle, move along a certain trajectory. And that produces, after some time, that may be randomly chosen, a new test model, m-test. And then we subject that test model to a metropolis rule. It is not exactly the metropolis rule of the Metropolis-Hastings algorithm, but it's very similar. If the metropolis rule rejects this test model, then we have to go back and start from scratch. Otherwise, if it's accepted, we just move on with exactly the same recipe. So we again kick the shuttle, it flies in a different direction, and we continue like this. So then I think you see where this is going. And each time, this momentum is drawn randomly. And so remember, in the null space shuttle, that momentum was drawn intelligently based on which kind of alternative models we wanted to construct. But in Hamiltonian Monte Carlo, you actually draw it randomly. And when you do this, you can actually prove mathematically that you then sample your posterior probability density. So key features of Hamiltonian Monte Carlo is that those trajectories that you produce, they loosely speaking always orbit around plausible models. In the picture that I have shown before, basically the Earth or the shuttle always stays near the sun. Right? It may go a little bit further or a little bit closer, but it is never totally removed. This allows it to basically make long distance moves. Long distance moves are still plausible because you sort of remain close to that attractor. And this in turn allows fast model space exploration. One may argue that a disadvantage is that you suddenly require derivative information. But in case it's not a big disadvantage because we have adjoint techniques. And with the help of adjoint techniques, we actually can compute those derivatives quite efficiently. So it's not a big problem. Now towards applications. And I want to show a specific one, which is the probabilistic full waveform inversion in just 2 dimensions. So we consider a 2D elastic wave propagation. We are using very simple finite difference method, a staggered grid method, simply because it's easy to implement. And we consider 3 different model parameters. Consider a p velocity, an s velocity, so velocity of shear waves, and distribution of density. The whole model, as you will see, has 10,800 grid points in 2 dimensions. So combined with those 3 model parameters that we have here, it means that the total model space dimension is 32,400. And this is a reasonably high dimension. So it is a dimension that starts to be geophysically interesting. And then we solve a synthetic problem. And only part of this is shown here. We're interested in a distribution of the s velocity and of density, and of course of p velocity. And the input models that we are using, they are shown here. So as I said, they're 2-dimensional. They are 125 meters in vertical direction, 200 meters in horizontal direction. And you see that the structure that we have roughly mimics some anticline structure that we may have inside the Earth. The sources are shown in the form of those beach balls at the bottom, and all the receivers are at the surface. And what we're trying to do is we are trying to basically reconstruct those input models, but we also want to have uncertainties that go with them. So, and indeed, if we use this Hamiltonian Monte Carlo sampling, we can, for example, reconstruct the means of those distributions, of those parameters. And what you see here is the mean model of shear velocity, which is very close to actually the input model, but also a mean model of density, which is not as close to the input model. And this is expected because traditionally, the recovery of density structure in seismic imaging is one of the big problems. It's one of imaging density is, I would say, one of the holy grails. This is something that we are not very good at because our data are not very sensitive to density variations. But still, you see that we actually recover something that we can, and that something in this case is the mean model of density. And of course, we may also look at other quantities. Then some expression of uncertainty that we may be interested in. There are many others, of course. The standard deviations of those model parameters. So shown here is, for example, the standard deviation of the S velocity. And yet you see basically that in some regions that standard deviation is rather high, say around 30 meters per second, for example, these regions. But there are other regions where the standard deviation is much smaller, maybe around 20, 15, for example, in these regions. And an interesting aspect here is that actually the uncertainties that you recover, uncertainty in the form of standard deviations, it's not the only way of quantifying uncertainty, of course, actually depends on the input model. And so you can actually see an imprint of the input model in the uncertainties. And this is something that only happens when the problem that you're solving is actually nonlinear. And when you go back to linear inverse theory, then you actually find that the posterior covariance matrix in the linear inverse problem, right, or the posterior standard deviations, they're independent of the model. Yeah. So your posterior covariance matrix, but also the resolution matrix, and so on and so forth, they are model independent quantities. But here you see with the naked eye that the uncertainties that you're quantifying obviously depend on the input model. Right? And this is something that only happens when your model is actually nonlinear. And here it's quite significantly nonlinear because that imprint is actually very strong. Well, in addition to the standard deviations of VS, of course, we also obtain standard deviations of density. And they're shown here. And you see that, that they're also quite substantial as expected. Right? So in regions where the model recovery or the mean model is very far from the target model, we also see that those uncertainties are very large. And it's well known because, as I said, recovering density information is a very difficult problem. Another problem that that I should mention at that point is that you can sample this high-dimensional posterior distribution, and you see that basically all we did with it on this slide, at least, is computing means and computing standard deviations. But of course, there are many. You have a flood of information, and we are condensing it into those very simple quantifiers. And so that means, in principle, we have a very advanced method, but I must admittedly say that we are maybe not making the most out of it, right? And trying to figure out how to actually define useful uncertainties for nonlinear inverse problems is, I think, one of the outstanding questions. And what is actually a quantity that you would like to look at in order to quantify uncertainty? And here we're looking at standard deviations, but as we all know, standard deviations may actually not mean very much when your posterior distribution is actually multimodal. Right? And how would we condense the uncertainty information that is contained in a multimodal posterior into a simple image that we may give to a geologist in order to help him to interpret this model in terms of local geology? And this, with all the technological advances that we have made, is, I think, something that at the moment we are not very good at. So if anybody in the audience has a good suggestion of how to improve this, I would be happy to hear this. So also for this chapter, some preliminary conclusions. We have seen that this Hamiltonian Monte Carlo is essentially a randomized version of the null space shuttle. And so the null space shuttle was a deterministic thing. We chose a certain initial momentum. The amplitude of it was constrained by the tolerance that we defined. And the direction was defined, for example, through a certain feature that we wanted to add or that we want to subtract. Now, Hamiltonian Monte Carlo does this differently. It chooses a random momentum vector in each iteration. And that random momentum vector is drawn from a Gaussian distribution, where the covariance matrix is actually the mass matrix or the inverse mass matrix of that null space shuttle. But it could in fact be drawn from a different distribution. And we have seen that, that we can already use this in order to solve 2D problems that may be interesting for geophysics or maybe even for medical imaging. We can treat order of magnitude 10,000 model parameters in 2 dimensions for 2-dimensional full waveform inversion, and actually without supercomputing. So Lars, who will present one of the later chapters, he actually ran that on his laptop. And so, of course, it doesn't go in a second, but it also doesn't take weeks. And that makes us quite hopeful that, that we're at least on track to apply this in 3 dimensions. What we obtain are both estimates of the parameters that we're actually interested in, but also of their attached uncertainties. And what is interesting, especially from a more applied perspective, is that we get estimates of density, which is a model parameter that is almost impossible to constrain when you're using a deterministic tomography. Because when you're running a deterministic tomography, the image that you get of density is very strongly biased by the regularization that you have to apply. And it's simply because the sensitivity of your observations with respect to density structure is so small that it is very easily overwhelmed by the regularization that you have to apply in order to make your inverse problem relatively well behaved. But of course, if you do Monte Carlo sampling of the posterior, there is no regularization that you have to apply. Right? And as a consequence, the images that you get of density, they may be miserable, but they are honestly so. And that honestly is because you actually have uncertainties that come with them. So you know how bad it is. And maybe there are actually patches of your model where the information that you get about density is at least to some extent useful. There's a question in the chat. I think I'll try to go there. In between or wait until the break. Yeah, if it's a question that I can answer quickly, feel free to ask that question just in between. If it's something that takes more discussion, then we maybe better leave this for the break.
Yeah, sure.
Just go ahead.
Okay, so my question is really around, so my background is, I used to be a petroleum engineer. Mm-hmm. So I'm looking at this from a sort of reservoir simulation perspective and mm-hmm. That kind of side. So, very far downstream of what I suppose you guys would be doing. But in terms of like the initial Hamiltonian spaceship idea, mm-hmm. like you were saying with the gas reservoirs, that sounds very interesting because, for like reserves, etc., estimation, mm-hmm. that would be something that would certainly be very interesting in terms of like putting some fake reservoirs in between and evaluating that. But also the sort of more guided approach would also be quite interesting because, with the spaceship, you're limited by what you are kind of coming up with in your mind, whereas the other one seems to kind of explore more sort of generalized things. So is there some kind of approach that, or have you thought about maybe combining the two to kind of weighted towards something that's more guided and generic?
Yes, of course. So basically this null space. So the null space shuttle would be on the deterministic end of the spectrum. Yeah. And Hamiltonian Monte Carlo would be on the probabilistic end of the spectrum. Yeah. But in fact, you can run this null space shuttle, for example, simply repeatedly.
Okay.
So you could let it, in some sort of semi-deterministic fashion, let it probe different random kinds of reservoirs that you want to add or subtract. Mm-hmm. Right? Or you can also play with those tolerances. Maybe you actually want to make your tolerance a bit higher, in order to see, what does it give you? Or maybe it gives you something that's interesting. So there are definitely shades of gray in between, where you can run this null space shuttle in a semi-random fashion in order to to say, probe different hypotheses, different random hypotheses, for example. So
okay.
there one can really be creative.
Yeah. As opposed as a sort of follow-up question to that, now this kind of seems like it would be creating like quite a few number of models, but
yeah.
obviously in the sort of from a production kind of perspective and monitoring kind of field, you wouldn't be able to have like 10,000 models and be able to maintain them, history match them against the production data. So you would want to perhaps collapse it down to
absolutely
like a number of models. Do you have some methodologies for that? For
so
like establishing some
so,
P10, P50, P90 cases?
Yeah, so we actually, I would say you have three different ones. The first one is simple subsampling. And so you solve Hamilton's equations. And to maintain numerical stability, your time step in the solution of Hamilton's equations has to be relatively small. But of course, within that small time step, you're not going to a model that looks significantly different. Right? So there's actually no point in actually looking at every single time sample. It's certainly enough to look at every hundredth. Right? So it's already that subsampling may reduce the number of models that you look at by 2 orders of magnitude. The other way of looking at it is, may sound a little bit silly, but simply looking at that movie. And so you can in a natural way produce those movies and simply see, is the alternative model that you produce actually reasonable from a geological perspective? But if you have a geologist looking at that, maybe he sees some alternative structure that the null space shuttle produced, and he just says from the outset that this is complete nonsense. Yeah. And I think it's simple, but I think this is a useful way of doing it.
No, absolutely. Yeah, I mean,
it's a little bit more quantitative. It's a simple algorithm that we devised. I can send you that. It actually allows you to find models that are at a certain distance from each other. And so you're not interested in models that are very similar to each other. You want to have models that are at a certain distance from each other. And that's basically what it's doing. You find one model that is good, and then it finds a model that is at least to a certain extent different. Right? And then you can iterate this. Yeah. Then what you end up with is a collection of models that is, of course, much, much smaller than the collection of all possible models, but they are as different as you would like them to be.
Yeah. Yeah, no, I think this is very interesting because it seems to be a very sort of generic approach that's not just for the waveform. Like you were saying, you could pretty much apply this to any kind of model.
Absolutely. It's totally not limited to wave propagation. And there are lots of variations of the theme, and one can really be creative.
Yeah.
So maybe a few words, why, more mathematical words, why does Hamiltonian Monte Carlo actually, why it is actually useful for inverse problems in relatively high dimensions? I sort of gave that intuitive explanation that you have this shuttle that makes long distance moves, but always remains in orbit around that planet, or around that attractor. But you can also show more quantitatively what the computational cost is for actually generating an independent sample. So for generating a sample that is not too similar to a sample that you have seen before. And you can actually show that for Hamiltonian Monte Carlo, this computational cost for generating an independent sample is proportional to n, which is the model space dimension, to the power of 5/4. So roughly speaking, the computational cost for generating an independent sample scales linearly, roughly linearly. Yeah, so as your model space dimension increases, of course, you have to compute more in order to find an independent model, but at least that more is roughly linear. For the Metropolis-Hastings algorithm, so really for the traditional Metropolis-Hastings algorithm, that scaling is proportional to n squared. And it basically means if you double your model space dimension, you compute 4 times more. And so it grows extremely fast. And that also explains why Metropolis-Hastings basically breaks down when your model space dimension is already mildly elevated. And I have not seen practical applications, at least within geophysics, where Metropolis-Hastings or variants of it have been applied to problems with a dimension that was significantly higher than 10, maybe 100. So the bottom line here really is that HMC is particularly well suited for high dimensional problems.
I have another quick question for the shades of gray. So when you say you're combining HMC with this idea of the distance and this null space shuttle idea, so are you entering then into something like approximate Bayesian computation where you have this distance and then you?
Oh, this distance is actually done a posteriori.
Mm-hmm.
Or well, not a posteriori, it's done on the fly. So the HMC is still correct. Uh-huh. It still produces this chain of samples, but instead of having to store an incredible amount of models, which you can't, you basically have an algorithm for subsampling.
Ah, okay.
Right? So on the one hand, of course, you can on the fly compute your posterior distributions and your means and your standard deviations and so on and so forth. But also on the fly, you can compute a subset of models that have at least that are at least at a certain distance from each other. Mm-hmm. And that basically gives you a subsampled collection of alternative models. And that collection will, at least in the examples that we had, be small enough to be stored.
Mm-hmm. Okay. Ryan also has a question.
Hello, can you hear me? Okay.
Yeah.
I'm always wondering, like, because these days, like, for example, like Metropolis Hastings or the other chain, this kind of like the Markov chain MCMC thing, they can try to expand it into the multi-chain. So it means that you start from multiple initial, multiple priori. So and then you will collapse it later. You will just stack off everything at once and then like put it in as your mean, and then like you can try to analyze from that one. Mm-hmm. And what do you think about like extending this kind of method into a multi-chain?
I think this is absolutely no problem. I think doing this is trivial because it's still a Markov chain Monte Carlo method, just like Metropolis Hastings or others. Just the mechanism for generating proposals is different. Right? So just as other Markov chain Monte Carlo methods can be run in parallel, so many chains in parallel, you can do this with this specific variant of MCMC. So there's no problem to this.
Okay.
Thanks. Okay. I want to go a little bit more into detail when it comes to this cost of generating independent samples.
Can I also ask one quick question? Probably a more simple one, because my background is that I have no background in this specifically. So I really like this intuitive explanation that you gave for the null space shuttle and also the Hamiltonian Monte Carlo. And I wonder if in the case of this randomized version, so the Hamiltonian Monte Carlo, if there's a problem if they are taking your image like 2 planets in our model space. So basically what I would consider 2 kind of peaks. If that causes problem in this sampling part?
So yes and no. So yes, in the sense of exploring a multimodal distribution that has multiple attractors is always more difficult than exploring a distribution which has a single attractor, simply because you may be stuck for a long time in a certain valley before you accidentally get out of it and see another valley. So that is the yes part. The no part is not something that is very intuitive, but you can prove mathematically that if you just wait long enough, you'll eventually see everything. What that long enough is, who knows? But this is a general problem of Monte Carlo methods. So if the valley that you don't see is just small enough, you wait arbitrarily long, on average.
Okay, thank you.
Okay, so before the break, I would say the first part of this lecture will be a little bit longer than the second, because I think we will be more tired later. So I want to enter this other topic, even though it will probably take me longer than 10 minutes. And it will be about this generating independent samples. And it turns out that, as a matter of fact, that all Monte Carlo methods have tuning parameters that steer the speed with which you're actually drawing an independent sample. Yeah, so I showed that very simple example at the beginning, where you do those baby steps. And if you do baby steps, of course, the next sample where you're going will be very similar to the one where you have been before. So the next sample will not be very independent from the one that you had before. Of course, if you then increase the step size, those models actually may become more and more independent. And of course, at a certain point, you can overdo it, and then nothing is accepted. Now, in Hamiltonian Monte Carlo, probably the most important thing that controls the extent to which you generate independent samples is the mass matrix. And the mass matrix is a very high dimensional creature. So if your model space dimension is n, then the number of elements in the mass matrix is roughly n squared over 2. So if you have a high model space dimension, say it's 1,000, then you suddenly have 500,000 tuning parameters. You can't do that by hand. So what is needed, not only in Hamiltonian Monte Carlo, but in many other Monte Carlo methods, is a way of automatically tuning your algorithm such that it produces independent samples as quickly as possible. And this brings me to the next chapter, which is on auto-tuning, which has an interesting double meaning, I found. Okay, so here it comes. So it's about drawing independent models, as I said. So there will be a little bit more motivation here. This is the actual challenge. Actually, under the hood, in all Metropolis Hastings, in all Markov chain Monte Carlo methods, this is the challenge: drawing independent models. Why is this important? It is important, obviously, for efficient model or null space exploration, because you don't want to generate lots of samples that all look the same. You want to generate samples that are different from each other. In other words, that are independent from each other. And also mathematically, actually the convergence of Monte Carlo integrals. So for example, the convergence of the posterior probability density, or the convergence of the mean that you compute, or of the standard deviation. This is proportional not to the number of models, not to the number of samples that you draw, but proportional to the number of independent samples. Right? So your error that you produce is proportional to 1 over the square root of independent samples. Right? If you draw many, many samples and all of them are dependent, it doesn't help you. What you need are samples that are independent. So here comes an example. It's a toy example, and it's from the sampling of a Gaussian distribution. Gaussians are boring, admittedly, but when you look at Gaussian in 1,000 dimensions, it actually starts to become interesting. And we look at a specific Gaussian that has a covariance matrix that is diagonal. And so if we look at our covariance matrix, C, it's a diagonal, everything is 0, except the diagonal elements. And the first one is 0.1, the last one is 1.1, and then we have a continuation between those, and everything is 0. So basically means the covariance matrix of the Gaussian that we're trying to sample has diagonal elements that vary by an order of magnitude. And then we do this Hamiltonian Monte Carlo, and the mass matrix that we choose is equal to 1. Right? So basically, remember what that means. It means that the kinetic energy of our null space shuttles is just 1 over 2 p transposed p. So, and then basically we want to know how many of the samples that we draw using Hamiltonian Monte Carlo are actually independent. And so if I draw, say, 1 million samples, how many of those are actually virtually similar to each other? And how many of those are actually different? There are many ways of quantifying this. And one way of quantifying this is the autocorrelation of the sample chain. And this is what you see here. So in the plot to the left, we look at 2 model parameters. And so we have a 1,000 dimensional Gaussian, and we look at model parameters M1 and M1000. And so M1 has this covariance attached 0.1, and M1000 1.1. And then we run this Hamiltonian Monte Carlo, and we draw many, many samples. And each sample has an M1 component, an M2 component, M3 component, and so on and so forth, all the way to M1000. And then what we compute is the autocorrelation of that sample chain. And that autocorrelation, which is a measure of the sample dependence, it's called A of k. It is literally the correlation of subsequent samples. And so you pick a component of your model vector, m, component m, and then you take the ith sample, multiply with the sample I plus k, and you sum over I. So it's literally the correlation of the chain of samples for a certain component of the model vector, so done component-wise. And then you simply normalize by the scalar product, or the norm of the model parameter. So this is what we see here to the left. So we see the autocorrelation of model parameter M1 plotted in black, and of model parameter M1000. So the autocorrelation for model parameter M1000, it pretty rapidly drops from 1 to around 0. And I would say it takes about maybe 50 samples or so. And so that means for model vector component M1000, you draw about, say, 50 samples, and then you actually see something different. But for model parameter M1, this is totally different. You draw many, many samples, so thousands of samples, but still the samples that you're drawing, for example, here, they're very strongly correlated to the samples that you have drawn before. Right? So basically, again and again, in one direction, you're seeing the same stuff. You're not seeing anything new. Right? You're just repeating yourself. So that the chain is highly correlated. So you're not producing independent samples. So based on this autocorrelation, one can actually compute an effective number of independent samples. It's like an exchange rate, if you will. So you have the total number of samples, n. You divide this by 1 plus 2, and then comes the sum over this autocorrelation. So you're just summing the wiggly lines that you see here to the left over all indices. Right? And this gives you an effective number of samples. And then you can divide this effective number of samples by the total number of samples. And this gives you the effective sample fraction. And it turns out that for the chains that you see here to the left, the effective sample fraction is 0.32 for model parameter M1000. And that roughly means you draw about 3 samples on average, and then you are independent. But for model parameter M1, this effective sample fraction is actually 0.04. That means you at least draw 200 samples before you're starting to see something that's different. And so that means, as I said, again and again, in M1 direction, you're seeing the same stuff. Now, this has an intuitive explanation. And this intuitive explanation is in this figure. We're looking here, let's at the beginning look only at the red curve that you see here. We see a 2-dimensional projection through our 2000-dimensional Gaussian. And we're looking, of course, at model parameter directions M1 and M1000. And what is shown here in red is a typical Hamiltonian trajectory. So it starts somewhere, it probably starts somewhere here. And then it oscillates through model space. And then what you see is that in M1000 direction, you're actually making rapid progress. Right? So let me choose a different color here. So in M1000 direction, you're making pretty rapid progress. So you're rapidly seeing a different part of model space. But in M1 direction, you're actually not making progress. Right? You're stuck. In M1 direction, you're hardly moving. Right? And this happens when your mass matrix is equal to the identity matrix. Now let's look at the second case. And the second case is when our mass matrix is the inverse covariance matrix of that Gaussian. And as I said, the mass matrix is in principle something that we're totally free to choose. The only requirement that we have to fulfill is that the mass matrix is positive definite. So if we do this, then we actually see that that Hamiltonian trajectory advances almost equally fast in all directions. Right? So in M1 direction and in M1000 direction, you're making progress that is roughly equally fast. And this is exactly what we want. So ideally, we choose a mass matrix for that Gaussian example that is the inverse covariance matrix. So more generally speaking, when we don't have a Gaussian, we can show that the ideal mass matrix is actually M, the mass matrix. It's the Hessian of the misfit or of the potential energy. And in the case of a Gaussian, that Hessian is the inverse covariance matrix. And so M equals H is the general case, and H equals C to the -1 is the special case of a Gaussian. So the problem, of course, here from a computational perspective is that the Hessian for a problem that is reasonably large cannot be computed or stored explicitly. It's simply too large. So, and here comes this idea of autotuning. And that autotuning is based on quasi-Newton methods, as I will explain. So the basic idea is to approximate the Hessian, or a low rank approximation of the Hessian on the fly, meaning as the Hamiltonian Monte Carlo is making progress in model space. And what we do is we use the last couple of samples that we have drawn in order to approximate not the full Hessian, but in order to approximate the Hessian times some arbitrary vector. And this is in fact all you need in order to execute the algorithm. You never need the Hessian or the mass matrix itself. You always need the mass matrix times some vector. Right? So there's no need to compute H explicitly. So what we do is we come up with a low rank approximation of H times some vector. What we do is very closely related to the LBFGS method from nonlinear optimization. A brilliant treatment can be found in this early paper by Nosedal or in his later book. And what we do is we use then the approximation of H that comes from the LBFGS method for M, for the mass matrix, in the computation of those Hamiltonian trajectories. Okay, so now with this, the concept still in pictures. So basically what we do, we have a zeroth approximation of the Hessian, which is the initial Hessian, which we just set equal to the identity matrix, and that we use as mass matrix. And then we go sampling our model space. So we come to a model M2, and based on model M2, model M1, based on those M1 and M2, we can come up with a new approximation of the Hessian, H1, which we set equal to the mass matrix. And then we continue sampling. Then we have M1, M0, M1, M2. And these we use to make a better approximation of the Hessian, which we call H2, and that we use as mass matrix. And then we continue. But at a certain point, we stop accumulating models, and we only use a handful of recent models. So for the fourth approximation in this toy cartoon here, we would forget about M0. Right, so that we would forget. And we would use M1, M2, M3, M4 for a new approximation of the Hessian, which we call H4. And then we continue, M5. We throw away M0, M1, and using M2, 3, 4, 5, we approximate H5, and so on and so forth. Okay? So with this, we return to our 1000 dimensional Gaussian that we have looked at before. So we have seen when we use the unit matrix as mass matrix, this autocorrelation plot of models M1 and M1000 that produced effective sample fractions of 0.32 and 0.047. And in particular, 0.047 is very, very low. So very few of the samples that you draw are actually independent. And if we use this quasi-Newton auto-tuning of the mass matrix, where we use an approximation of the Hessian S-mass matrix, we actually see that also model parameter M1 starts to decorrelate very quickly, right, after about 20 samples. Right? And indeed, we see that then our effective sample fraction is nearly equal for both models. It's about 0.17 for model parameter M1000 and 0.14 for model parameter M1. And this is acceptable in both cases. Of course, for model parameter M1000, this has reduced a little bit, but this is something that we can live with, given that the effective sample fraction for model parameter M1 has actually increased by 2 orders of magnitude. Here's a more interesting example. It's a 1000-dimensional Stiplinsky-Tang function. It's an analytical test function frequently used in nonlinear optimization. And this pretty creature has 4 to the power of 500 local minima. And what you see here to the left is just a 2-dimensional projection, again through model parameters M1 and M1000. If we do not use auto-tuning, we again see that model parameter M1 remains very highly correlated for a very long time, meaning that in M1 direction in model space, you hardly draw independent samples unless you draw many, many samples. But if auto-tuning is turned on, so this LBFGS-based auto-tuning, then you produce largely uncorrelated models also for M1 after, again, about 20 samples. So it works even when you're not sampling a boring Gaussian. And of course, this also translates to improved posterior distributions. If auto-tuning is turned on, then you actually manage to sample this local minimum that you have here. If auto-tuning is not used, you actually miss it because you have not drawn sufficiently many independent samples. Okay, so towards something that's a little bit more interesting, that is a 1D viscoelastic full-waveform inversion. It's 1D simply because I wanted to have a toy problem that shows the functioning of this and that I can run on my laptop. So the setup is as follows. We are interested in a 1-dimensional viscoelastic wave equation. So we have here frequency omega squared times u, which is the displacement field. This is the actual wave field as a function of frequency and position, plus c squared. This is the distribution of velocity. It's actually a complex valued velocity, times the second space derivative of the wave field. And this is equal to some external forcing term. The model parameters that I'm interested in are 2. There's the real part of the logarithmic velocity. So we divide the real part of this velocity by some reference and take the natural logarithm. This is the first model parameter that I'm interested in. And the second model parameter I'm interested in is the logarithmic attenuation. The first one was logarithmic velocity. And for this, I divide the imaginary part of velocity by some reference, and I take the natural logarithm. This may seem unnecessarily complicated. Why don't we just look at velocity and attenuation? But there are very good reasons for this. Obviously, for both velocity and attenuation, it is equally justified to work with their reciprocals. So to work with 1 over velocity and to work with 1 over attenuation. They're equally good. And the beauty of looking at logarithmic velocities and logarithmic attenuation is that that subjective choice actually becomes irrelevant. They're both Jeffreys parameters, so you can replace them by 1 over the parameter itself. But if you do this, all probability densities actually remain invariant when you're using, those logarithmic quantities. And this is a nice thing to have. And also, when you're using logarithmic quantities, you can actually use Gaussians as probability densities, which otherwise you're not allowed to do because they're positive quantities. And I want to show you that in this case, to sample such a 1-dimensional full waveform inversion, auto-tuning is really an absolutely essential thing because the sensitivities with respect to velocity, the real part, and attenuation, the imaginary part, vary by orders of magnitude. So you have one model parameter that is vastly less important than another. More to the setup, we are running a synthetic test where the true model is shown here in black. So it's a one-dimensional profile. In x direction, we have kilometers, x in kilometers. In y direction, you have the actual quantities. The true, so the input is in black. The initial is in red, so it's a smoothed version. And then we compute frequency domain wave fields. And two examples are shown here. The first one is for low frequency, 0.02 hertz. The artificial wave field, so the observed wave field artificial, is shown in black. And the synthetic wave field for the initial model is in red. And you see that they are different to some extent. All the triangles, the red triangles, these are the observations at the receiver positions. So observations of the wave field at the receiver positions. And all the sources are shown in the form of stars. Right? And so the wave field that you see here is the wave field for the source that is shown here with the biggest symbol. And below is another example at higher frequency. This is for 0.32 hertz. And there you see that actually observations and synthetics differ very substantially. Well, then we run this Hamiltonian Monte Carlo with auto-tuning. And one of the things that we can recover are, for example, those one-dimensional marginal distributions for all 2000 model parameters. So we have 1000 velocity parameters and 1000 attenuation model parameters. And the posterior distributions for the logarithmic velocity, they're shown here on the left as a function of position. And then you very nicely see that you have some regions, for example here, where your posterior is multimodal. And so you have different solutions that cluster here, or solutions that cluster here. And both kinds of solutions actually explain the observations. So you're actually properly sampling a multimodal, high-dimensional probability density. To the right is shown the imaginary part of logarithmic velocity. I don't want to go into much detail, but what I want to point out is that those posteriors are very broad, which means it's not unimportant. Even when you run a full waveform inversion, attenuation is very poorly constrained. So your uncertainties remain very large. An important thing here, before I come to the conclusions, is that the effective sample size, when auto-tuning is used, is more than 10,000 for all of the 2000 model parameters that we're interested in. And if you switch off the auto-tuning and just use the identity matrix as mass matrix, it actually drops below 100 for some model parameters. So it becomes useless. And the point here is that auto-tuning is really essential in order to tackle this problem. Good, so some conclusions here as well before we go into the break. In the introduction, I have shown you that Monte Carlo convergence, this is very well known, you will find this in all Monte Carlo textbooks, very critically depends on the number of independent samples, not on the number of total samples that you draw, but on the fraction of those that are actually independent. And in the case of Hamiltonian Monte Carlo, the sample independence can be steered, can be controlled through the choice of the mass matrix. The ideal mass matrix is the Hessian, which is the second derivative of the misfit functional, or the second derivative of the potential energy. And for reasonably large problems, this cannot be computed or stored explicitly. So what we do in the auto-tuning is we approximate the local Hessian, or Hessian vector products to be more precise, using a quasi-Newton method. And the specific one that we use here is actually a factorized version of the very well-known LBFGS method. So low memory BFGS method. And that uses just a small number of previous evaluations of the misfit and the gradient. In numerical examples, so both analytical functions and this 1D full waveform inversion, we have seen that this auto-tuning can help to increase the effective sample size really by orders of magnitude. So it can be decisive between an algorithm that is uselessly slow and an algorithm that actually performs to an extent that is useful. We have seen this application in 1D viscoelastic full waveform inversion. Admittedly, it's a toy problem, but it's useful because it teaches you something not only about the algorithm, but actually also about physics. There we have seen that the auto-tuning is absolutely essential to actually make it run. And it also nicely recovers the multimodality of the solution, which is something that with a deterministic approach, it would be very hard to get. And also, and that is a little bit disappointing here, is that there seems to be little hope to actually constrain attenuation, even when you run full waveform inversion. And with this, I think it's good time for a break, maybe for a little discussion, for a cup of tea or a cup of coffee. So if you have any questions, please feel free to ask them. And then I would suggest that we continue maybe in half an hour.
Okay, thanks a lot. Yes, directly some questions, George. I was guessing so.
Thanks for the talk. How do you efficiently calculate Bayesian, and how does the computational efficiency compared with the original Hamiltonian when you consider the Bayesian?
Sorry, I didn't understand the second part of the question.
So how does the computational efficiency compared with the Hamiltonian Monte Carlo without the Bayesian?
Okay.
Yeah.
So the efficient computation here really is through the LBFGS method. So what we compute is actually, or what we approximate, is not the Hessian itself, but Hessian times an arbitrary vector. And this is all you need. So in order to execute the Hamiltonian Monte Carlo algorithm, you never need the Hessian itself. You only need Hessian vector products, right? And basically the efficiency here comes from approximating this quantity through the LBFGS method, right? So LBFGS is a method from nonlinear optimization. It's a quasi-Newton method. So it mimics a Newton method by computing approximate Hessian vector products. And it is efficient because all that you need for this approximation is a couple, so I would say order of magnitude 10, evaluations of the misfit and of the gradient. So what you do is you sample, you march through model space, and you store the 10 last evaluations of the misfit and of the gradient. And so something that is relatively easy to store. And based on those, say, order of magnitude 10 evaluations of the misfit and the gradient, which is easy, you can approximate this quantity. Okay, so here really, I can't write down the LBFGS method here because it would be too long to explain. But I would really recommend to go to this classic paper by Nocedal from 1980. It's very understandable, and it outlines the method and explains how the evaluation of those models that you see here and the gradients at those model positions actually allows you to approximate this Hessian vector product very efficiently. So the computational overhead is very, very small. Mm-hmm. And so then how does the efficiency compare to not using the Hessian? Well, this is really in this statement here in the effective sample size. So efficiency is what is measured in terms of the effective sample size. And so the effective sample size is the number of models of models that you draw, of samples that you draw, that are effectively independent. Right? So the effective sample size is a measure for the number of models, of samples that are actually independent. Right? So you may draw, say, 1 million samples, but many of those samples will look very similar, so they will be dependent. And
yeah, but without
the effective number of models that are independent is quantified by that effective sample size. And this auto-tuning, so this use of the LBFGS Hessian, allows you to sometimes increase that effective sample size really by orders of magnitude, meaning that you can literally speed up the algorithm by orders of magnitude.
How does that compare? Maybe George, you can say that as well, to the approach by Omar. Andreas, do you know?
No, maybe explain the approach that Omar has.
Omar Gattas in this, he's using the Hessian as well in the action on the vector.
What I have seen is that they are actually using it in order to approximate the Gaussian.
Yeah.
Right, so there the idea would be that you forget about the fact that your posterior is actually multimodal.
Okay.
Right, so you think you're located in a basin of attraction that you like, and you say, okay, this thing is roughly Gaussian.
Yeah.
Then you want to know the properties of that Gaussian, and that Gaussian can be linked to the Hessian.
Yeah.
And you can basically approximate that. You can't approximate the Hessian itself, but using LBFGS, you can approximate Hessian vector products. And then from Hessian vector products, you can reconstruct properties of the Hessian itself.
Yeah. That's exactly.
So it's like, I would say it's a subset of this broader class of methods in Hamiltonian Monte Carlo, which of course becomes more efficient, provided that your posterior is actually really closely to being Gaussian. And so that there's a little bit of no free lunch here. And if you actually know that your posterior is roughly Gaussian, then of course Hamiltonian Monte Carlo may be an overkill, right? But if you're actually not sure and it's multimodal, then Omar's method may still be more efficient, but it'll give you the wrong answer.
So in this 1D example, can you go back to this just a couple of slides back? Where do these, especially in the imaginary part, where do these peaks come from?
These are actually the source locations.
Ah, okay, so that's an effect. Yeah. Okay.
Yeah.
Interesting. Yeah. Okay. Yes, but it's really nice to see this multimodal distribution on the left. Andrea, there's a question.
Hi, yes, thanks. This is all very interesting. I had a question, especially with this multimodal slide. I'm having trouble imagining this in 2D. Like, how would the other dimension?
Yeah, it just becomes a nightmare to visualize, of course. So in 2 dimensions, maybe I changed the pen color here. I'm running out of colors. Green. Okay. So so in 2 dimensions, we would have a 2-dimensional model. So you would have a y direction, y, and an x direction. But then you would not be able to plot the posteriors in this way. And so for each pixel, you would actually have to plot a 2-dimensional distribution that may be multimodal. You know, maybe have 3 modes. And so here in 1 dimension, I have the benefit that that was actually wrong. Sorry. For each model parameter, for each pixel that you have here, you would end up with a certain distribution. So this might be model parameter, whatever, M18, right? And then M18 may have a certain distribution, a certain 1-dimensional posterior, which may be something. Right? So in principle, you would have to plot that creature for each of the model parameters that you have in your 2-dimensional model. And so you run into a visualization problem. So, and this is not, it's actually an important problem. And it touches on that more fundamental question of how do we actually visualize, how do we convey uncertainties, because they're such high-dimensional creatures that we run into visualization problems, and we run into thinking problems because we can't think in more than 3 dimensions. And in my opinion, this is a somewhat open question.
Yeah.
So your question is basically a special case of that more general thing.
Yeah, it's something to think about, definitely. We run into these visualization problems all the time, and yeah, I really like it in the 1D case though. So
yeah,
I think
it's still pretty, but already in 2D you're in trouble.
Yeah,
and maybe, I mean, one way of doing it is maybe, of course, you can always look at individual parameters. You may look at linear combinations of parameters, or you may use this kind of Monte Carlo methods to actually do hypothesis testing and say, okay, how likely is it that your model looks like that? But most likely the answer is very application specific.
So just a quick follow-up, Tristan, before I get to you. Did you try entropy as a measure for the distributions?
Oh yeah, absolutely. So so this is what we did for the analytical case. So for example, for the Stiplinsky tongue function and for the Gaussian, where you can literally measure the distance between the analytically given distribution and distribution that you approximate through sampling.
But that's been with KL divergence.
Exactly.
But entropy of the distribution itself, so as a measure of uncertainty, I mean, if you have like a multimodal distribution, you could still calculate it.
No, I have not used it. Yeah, but it's a good idea. Yeah.
That's something which we've been using quite successfully for discrete cases. That's easy. But also the same problem that if we have multiple realizations of geological models and we have classes, that it's still something which is difficult to visualize. And so we've been using entropy quite successfully for many years. In the continuous case, it becomes more tricky because you need to find some sort of a binning or number of kernels to estimate it. But there are nice ways to do that.
Okay, yeah, good idea. Yeah.
Tristan?
Yeah, so I was just wondering if you would perhaps mind just giving a sort of, I wasn't quite sure on the initial space shuttle idea how you actually perform each of the iterations. So like, I know it doesn't really matter what the model is, but in terms of, what do you actually need to sort of calculate, I suppose, behind the scenes in order to move from the initial state to the next? Would you perhaps mind just rolling back on that?
Yeah, let me go back a few slides. So basically, you have to solve Hamilton's equations. And so what you have, or what you want, is model M as a function of time. And you basically see that the time derivative of the model is equal to the derivative of the Hamiltonian with respect to the momentum. And then, so you have H depending on M and P. And then the P component, the time derivative, is equal to the negative derivative of the Hamiltonian with respect to your model parameters. So you have those two ordinary differential equations, which are Hamilton's equations. And you basically solve them using some numerical method that you like. And what we used here is the leapfrog method. So it's basically, if you will, it's a finite difference method to solve Hamilton's equations. So basically, you start with some M0, and then with the leapfrog method, you compute for M of T0, you compute M of T1, M of T2, and so on and so forth. So you basically discretize this ordinary or those ordinary differential equations in time, and then you hop forward in time. And of course, there are tons of ways of doing this, and the method that we used is leapfrog, but there are many others that are possible.
Okay. Yeah. Okay. So in terms of for the derivatives now, if the model isn't analytical, I suppose, then you would have to generate numerical derivatives. So depending on the number of variables that you have and the time taken for the simulation, that would be quite time intensive, I suppose.
Yes and no. So first, what you're saying is of course right. So the the numerical difficulty is hidden in this term. So the derivative of the Hamiltonian with respect to model parameters, this is actually equal to the derivative of the misfit, chi, with respect to model parameters.
Mm-hmm.
Right, so, and for this, we use adjoint methods. And the beauty of adjoint methods is that that you can get this derivative, or say this this gradient, so the full derivative vector, no matter how big the vector is, with one forward and with one adjoint simulation. So in the case of wave propagation, you basically run one forward simulation and you run one adjoint simulation, which is, since it's almost self-adjoint, basically the same as a forward simulation. And based on those two simulations, you get the gradient vector, no matter how many components it has. Right? So your numerical cost of computing that gradient is independent of the model space dimension. And so you have the numerical cost that is clear, but it is dimension independent.
Okay, so like even I suppose if you were, let's say your model was like a reservoir simulator and you were doing some history matching, you would just have to rerun the full history twice essentially to get the derivative.
Correct.
Okay. Yes. Well, that's very promising then.
So and then of course you can do all sorts of tricks. So for example, you may want to do a sloppy null space shuttle, and maybe you don't need derivatives that are terribly exact. And so maybe you can save computational time by, for example, running a simulation that is under-resolved in order to get a derivative that is approximately right.
Yeah, yeah.
So there's a whole body of literature. There's a whole bunch of dirty tricks that you can do in order to make this more efficient.
Yeah. Have you seen these kind of Hamiltonian space shuttles being applied for reservoir simulation?
No, not yet. No. I mean, we published a paper on this, I would say, about 1.5 years ago. We see that it's starting to be picked up, that people find it interesting, and I think also conceptually interesting. But in that specific discipline, I haven't seen applications.
Okay. In terms of the kind of complexity of the models that you've tried, how long would you say like a single forward iteration or a single evaluation of the model takes, roughly?
So it depends a lot on the computational expense of your forward problem, really.
Yeah.
So for the nonlinear travel time tomography that I've shown you, it's a matter of seconds. So
okay.
It's a matter of seconds on a laptop.
Okay.
Of course, then if you run a 3D full waveform inversion, then it may take minutes to hours on hundreds of cores.
Okay. Yeah. So quite considering. Yeah.
So,
okay.
So you have the whole spectrum, really depending on the expense of your forward problem.
Yeah. Yeah. Unfortunately, computation is always the bottleneck with these.
Yes. So the null space shuttle is somewhere in between, right? Of course, it's more expensive than coming up with a single solution, but it's still orders of magnitude less expensive than running a full-blown Monte Carlo simulation.
Yeah. No, absolutely.
So it's in between, but of course, uncertainty quantification is never cheap.
Yeah, no, I mean that's something I've come across a lot when I was working in the industry. Companies setting up like whole Azure and Amazon Web Service environments to run like their 200 realizations of their model.
Yeah.
So.
Okay, so let's give Andreas a couple of minutes of a break. And then we continue.
I'll get a coffee and then I'll be back in 10 minutes or so.
Yes, see you all in a bit.
A lot. Okay, I tried to find attractive pictures to keep people.
That's fantastic.
to wake people up.
Yeah, exactly.
Every 20 minutes.
Maybe another one which is called Coffee SEM then.
Next time.
or smoothie with a coffee shot here. So Lars is going to present that part?
No, that I'm doing, and Lars will do the next.
That's the next one is then on the neural networks. Okay, yes. Fantastic. Let's see, Tristan, you still have your hand raised. If you can continue asking, but just there's no confusion.
Yeah, Lars is just asking me. So when it's his part, could he share his screen? I think that would be the easiest. We have the same presentation here. And
so just we can just make him host maybe as well.
Yeah, and then I would just hand over to him for the next chapter.
Yes. I cannot make him host because I'm not a full host.
I do.
Okay, thanks, Monica, you're still here. Fantastic.
It's always, you know, as professors, we think we have competences, but we actually don't.
Yes. You always rely on the people who actually do the work.
In the end, it's always your assistant who keeps things running, right?
Yes, as we see here.
Yeah.
Okay. So I think we can continue. Huh? Yeah.
Good. Yeah, perfect. So, the first few chapters, they were essentially on sampling the null space, on sampling a probability density, and as was mentioned in the discussion, actually, all of this, of course, rests on the speed with which you can actually generate a single sample, which means on the speed with which you can actually solve your forward modeling equations and also the adjoint equations that you need in order to compute a gradient. So the chapter here is exactly about this. It's about a strategy that allows us to accelerate forward and adjoint simulations using a specific method that we call smoothie SEM, but it's more appropriately called a spectral element method that uses wave field adapted meshes. So here's the idea. The basic concept can be explained most easily, as so often, in 2 dimensions, where we may use such a regular finite element mesh in order to propagate a wave field from a source towards some receiver. That wave field propagates through a heterogeneous medium, which you see here on the right, in the form of this grayscale. So it's variable in both p and s velocity, and the p and the s waves are shown here in different colors. As is well known, a certain number of elements is required per minimum wavelength in order to make sure that you actually have a good numerical accuracy, so a useful solution. Now, what is not so obvious is that wavelengths that we have here, so minimum wavelengths, that wavelength is actually an anisotropic quantity. And it's very easy to see. So in fact, wavelength varies much more rapidly parallel to the propagation direction, but it actually varies pretty slowly perpendicular to the propagation direction. So, and that anisotropy of wavelengths can actually be exploited in order to reduce the number of elements that you need in order to obtain an accurate solution. And this is what is shown here to the left. You see a numerical mesh that looks totally different. It is in fact centered around the source and has a certain azimuthal symmetry. And this mesh, which is adapted to the complexity of the wave field, or to our prior knowledge of the geometry, of the approximate geometry of the wave field, uses about 8 times less elements than the regular mesh that we have above. So the regular mesh that we have here has 10,000 elements. The wave field adapted mesh that we see here below only has 1,250. But yet you see the numerical solutions that you produce for both cases are basically identical for all practical purposes. Of course, the number of elements in azimuthal direction need not be fixed. It is something that you can adjust. And in fact, it should be adjusted as a function of the medium complexity. So if your medium is very smooth and very or close to being homogeneous, then you may be able to use a very small number of elements in azimuthal direction. But if your medium is more complicated, the number of elements in azimuthal direction probably has to increase. So it's kind of problem dependent. Now this can actually be extended to 3 dimensions by using, again, wave fields that have a certain azimuthal symmetry. So in contrast to having the cubed sphere mesh that we see here to the left, with about 400,000 elements, we could actually use a mesh that is azimuthally or rotationally symmetric around the position of the source, and then has only a certain number of elements in azimuthal direction. Right, so this mesh that you see here is actually downsampled for visualization, would be good for propagation of waves with a minimum period of about 100 seconds. And instead of about 400,000 elements, it has about 36,000 elements. So an order of magnitude less. And of course, this means that your computational expense for actually running a wave propagation in this wave field adapted mesh is about 10 times less than for the regular cubed sphere mesh that you see to the left. This can be done in even more extreme ways. For example, in some cases, you may only be interested in a certain part of the Earth where you have receivers. And then, of course, you could go as far as chopping off those parts of your mesh where your receivers are actually not located, so where there's no interesting part of the wave field. And then you not only have wave field adapted meshes, but also coverage adapted meshes. And depending on what your coverage is, this may lead to quite substantial savings. But again, this is obviously application specific. Now, here comes something that is less trivial, which is how to actually run adjoint simulations for such scenarios, for such wave field adapted meshes. So we want to compute sensitivity kernels for, say, a setup that we see here. So we have a certain number of sources. These are all the yellow stars, and receivers, which are all the red triangles. And we're interested in a synthetic inversion where we try to recover the input model that we see here to the right. So what we do is we start with a regular mesh that we see here symbolically. Our domain is 1,400 kilometers in each direction. And we have a source that emits a wave field into the medium. And again, as before, we were looking at an elastic medium. So you see a slow S wave and a faster P wave. So we have a forward wave field that radiates from the source to the receivers using, for example, a spectral element method. Then we have adjoint sources that are located at the receiver positions. And so one of the receiver positions is, for example, here, right? And that receiver position radiates an adjoint wave field. There's another receiver position that is here that radiates this adjoint wave field, right? Another receiver position is here. It radiates the adjoint wave field that you see here, right? And each of those radiates the residuals. So that is the difference between observations and synthetics back into the medium. And then what we do, and this has been known for almost 40 years, we compute the product of the forward and the adjoint wave fields. We integrate that product over time, and this produces a sensitivity curve. So this is basically the volumetric density of the derivative. And so this is easy. But now we're actually not using regular meshes. We are interested in using wave field adapted meshes. So this wave field adapted mesh can be used to again radiate a wave field from the source around which this mesh is centered into the medium. Right? And by construction, the wave field that we produce, the forward wave field that we produce with this wave field adapted mesh, is practically identical to the wave field that we produced with the regular mesh that we see below. So this is all fine and good. The problem now comes when we consider the positions of those adjoint sources, for example, here and here and there. Because now, at the position of those adjoint sources, for example, at this one, which may be roughly up here, the mesh is extremely coarse, right? So it's actually not centered around the adjoint source. So the mesh is not made for the adjoint source. The mesh is made for the regular source from which we are radiating the forward wave field. But maybe let's forget about this for a moment, and still let's use the wave field adapted mesh in order to radiate the adjoint wave field back into the medium. And as expected, since this wave field is not centered on adjoint sources, but centered on a specific forward source, the adjoint field actually doesn't look correct. And so the adjoint field, in contrast to the forward wave field that we compute here, looks very different from the adjoint wave field that we have computed for the regular mesh. And this is expected because that mesh, in those outer regions here especially, is much too coarse and not at all tailored towards the geometry of the adjoint field. But then magic happens. We again take this forward wave field, we multiply with this adjoint wave field, then we integrate over time, and out comes the correct sensitivity curve. Okay, so this may seem kind of surprising. So we have used an adjoint wave field that seems incorrect, multiply it with the correct forward wave field, and even though the adjoint wave field is apparently, let's say apparently, incorrect, we actually obtain the correct sensitivity curve. So what has happened? What's going on? How can this be? In fact, it's very simple. We are looking at a discrete forward problem. We're using a numerical method. So we are solving a discrete version, a discretized version of our forward problem. And here we are using a specific spectral element discretization, namely a spectral element discretization that uses a wave field adapted mesh that is centered on the position of a specific source. Now, this discrete forward problem can be written in the form of L times U equals F. L would be a discrete forward modeling operator that we obtain through the spectral element discretization of our wave equation. U is the discrete forward wave field that we're interested in, that you saw in pictures. And F is a discrete forward source. So we solve this matrix vector equation symbolically, and then obtain the numerical wave field U. Now we can apply the adjoint method. Most of you may maybe know the continuous adjoint method, but we actually apply the discrete version of it. And so we obtain the exact discrete adjoint problem. So the exact adjoint of that discrete forward problem. And that exact adjoint of this matrix vector equation is written down here symbolically. It uses exactly the same discretization, right? So the discretization is attached to L. It's this wave field adapted mesh. Then we compute the adjoint or the Hermitian transpose of L, which is L star. Right? These two belong together, times U star, which is the discrete adjoint wave field. That is equal to F star, which is the discrete adjoint source. And this is exact. It's the adjoint of this discrete forward problem. Now what happens is that when you plot U star, so the discrete adjoint wave field, it looks odd. Right? It's basically that apparently incorrect solution that we have seen before. But it really just appears strange when we visualize it. But this has nothing to say. Right? It is still the correct discrete adjoint field. If this looks strange when you plot it, absolutely does not matter. Right? So, and here one really has to remember that an adjoint wave field is not a physical quantity. Right? It's just an abstract mathematical construction, and they absolutely do not have to be physical or do not have to have physical meaning. Yeah, so you get the correct discrete adjoint wave field. It just looks strange, but it is really still the correct adjoint. So the point here is then that we can, for this wave field adapted mesh, actually compute the exact gradients without having to generate a new mesh for all the adjoint sources. And with this in hand, we can actually run full waveform inversion. And what you will see first is a 2D toy example, just to show you what the potential of this is. So we run the synthetic recovery test. We have already seen the setup. So we have sources and receivers to the left, and we try to recover the heterogeneous input model that we see to the right. And our initial model is homogeneous. And our goal here was to reduce the initial misfit by at least 95%. And it turns out that in order to do this with this regular mesh that we see here, we needed 66.6 CPU hours. If we want to achieve a 95 misfit reduction using wave field adapted meshes, and of course then you have a different mesh for each of the sources that you're using, we're only using 6.2 CPU hours. So note, this is more than an order of magnitude less computing time required to solve this full waveform inversion problem using wave field adapted meshes. And yet, the models that you recover, shown here below, they're virtually identical. Yeah? So you have a 1 order of magnitude reduction in computational expense for the same recovery. So this can be transported to 3 dimensions. And what I want to show here is actually an application to a deterministic global scale full waveform inversion, which is pretty advanced already, I would say, but still work in progress. Our main goal is to construct a long period reference model of the Earth, of the whole Earth, that includes ideally data from all earthquakes for which we have moment tensor solutions available. And it is typically for earthquakes with a magnitude above 5.5. We want to have this model to properly account for wave propagation through 3D heterogeneous medium, to account for topography, oceans, crustal variations, but also for finite frequency sensitivity. So the data set that we have at the moment contains 1,200 earthquakes, and it's gradually expanding. And for each of those earthquakes, which acts as a source, as I explained at the very beginning, we have 3,000 to 4,000 recordings. So it's a pretty massive data set. The minimum period that we are considering at the moment is 80 seconds. And we assimilate complete waveforms, that is for 3 components, and every wiggle that we find useful, including body waves and fundamental and higher mode surface waves. Now, some technical details. The initial model that we're using is radially symmetric. It's the well-known preliminary reference Earth model, PREM. And for the optimization, we use, again, an LBFGS method, but a stochastic gradient version of it. So the preliminary results are shown here. What we see is our S-velocity distributions. So to the left, these are the velocities of SH waves, so horizontally polarized S waves. And to the right, the propagation velocities of SV waves, so vertically polarized S waves. And this is plotted here at different depths, 150, 1,000, and 2,500 kilometers, but it's a continuous model. I don't want to go into the details of those models. The interpretation is really not the focus of this more technical mathematical presentation. The point I want to make is actually the computational cost. So if we had used a standard global finite element mesh, as I have shown a few slides before, the whole exercise, so the computation of the model that you have seen before, would have required about 1.4 million GPU hours. The study of Bostock and co-workers from a few years ago that achieved a resolution that, at least visually, was a bit lower than what we have, required 320,000 GPU hours. And the work of Lay and co-workers last year that again, visually achieves a resolution that is quite comparable to what we have, required 1.1 million GPU hours. And then with those wave field adapted meshes that we are using, we reduce this to less than 15,000. So you see that the reduction in computational requirements is really very, very substantial. It's actually going quite a bit beyond an order of magnitude. So it makes a very significant difference. So here to conclude, those wave field adapted meshes, they are meshes, finite element meshes that are designed on the basis of prior knowledge that we have about the geometry of the wave field. And especially when the medium that we're considering is relatively smooth, our prior knowledge about the geometry of the wave field is actually pretty good, because we know that waves radiate roughly concentrically around the source. So we know roughly what the geometry of the wave field will be, and we can then tailor our mesh according to that prior knowledge. Right? So again, going back to no free lunch, the no free lunch theorem that I have briefly mentioned before, what makes this method efficient is not the method itself, but it's the method combined with prior knowledge that we have here specifically on the geometry of the wave field. Now, the complexity of the mesh is basically controlled by the number of elements in azimuthal direction. And this is something that we can adjust. And so we can, before running a full-blown full waveform inversion, we can run a couple of checks where we use a full mesh, a regular mesh, and an adapted mesh, a wave field adapted mesh, such that the wave field adapted mesh actually reproduces the solution for the regular mesh. Right? And then depending on the complexity of the medium, we may want to adjust the number of azimuthal elements. And the medium is very harmless, very smooth. That's why the method is called smoothie SEM. We may get away with a small number of elements in azimuthal direction. But as the medium becomes more and more heterogeneous, we may want to add elements in azimuthal direction. So this is what I just said. It works best for smooth models, or that is for tomographic models, or differently speaking, for models, for tomographic models that we typically obtain at regional or global scale. And again, this is why it's called smoothie SEM. And as I said, through the use of discrete adjoints, this concept can actually be incorporated into full waveform inversion schemes. Because contrary to what one may expect, we do not have to redesign finite element meshes for the adjoint sources, which are at the receiver positions, but instead, we can actually just use the wave field adapted mesh adapted to a specific forward source and simply use this for the adjoint simulations. And the discrete adjoint method then tells us that we still get the exact sensitivity currents. So what this effectively does, at least for models that are relatively smooth, so that is at regional or global scales, we effectively reduce the dimension of the forward problem by 1. And this is why it becomes so computationally efficient. Then I have shown you a preliminary global scale application. We really tend to work towards a long period 3D reference model of the Earth on a wave propagation through 3D heterogeneous medium, correctly account for topography, oceans, crustal variations, and so on and so forth. And the long-term goal is to include complete waveform data for all earthquakes with magnitude above about 5.5. So far we think that results are really encouraging based on that large, but still smaller than we intend data set of 1,200 events. And what we have seen so far is that computational requirements are 1 or even 2 orders of magnitude smaller than in similar studies that are somewhat comparable. But of course, one is always to some extent comparing apples and oranges, but still the message holds that the computational savings are very, very substantial. So with this, I would like to end this chapter. If you have any questions, please feel free to ask them. And then after this, I would hand over to Lars.
Yes, thanks. We have a question from Tristan again, or did you? It's not raised before, yeah.
Yeah, hi. When you say long-term simulation, do you mean kind of like a sort of continuous simulation, or would you, for the 1,200 events that you have, would this be a simulation of each event with the model being kind of reset to a sort of initial condition in between, or is it a sort of continuous simulation?
Yeah, no, I think that, no, probably I didn't express myself very well. So we are at the moment we are using 1,200 events that we simulate for the whole globe. So 1,200 earthquakes, but the long-term goal is really to expand this to include all earthquakes with a magnitude above about 5.5, for which we have global scale data. Not sure I answered the question correctly.
Yeah, I think you did. Yeah, essentially you're kind of simulating each event in isolation.
Yes.
Yeah. Okay.
Yes.
The other question I had is with the wave field adapted meshes. I kind of, maybe I misunderstood this, but it's mainly around the sort of formulation of the gridding, kind of like optimizing the gridding for the simulation and getting the gains from the simulation that way.
Correct.
Okay.
Exactly.
Yeah.
So the idea is usually when we run wave field simulations, we have the same mesh for all the sources that we're using.
Yeah.
And the mesh does not harness the prior information that we have on the geometry that the wave field will actually have.
Yeah.
And so prior information basically remains unused if we use generic meshes that are equally good or bad for all sources. Mm-hmm. So it's, in a way, it's a classical example of making an algorithm more efficient by actually exploiting prior knowledge.
Mm-hmm. Yeah. So I guess that kind of leads to my well, hopefully final question on this part. I mean, the sort of mesh building is, it's always, particularly in the oil and gas industry, it's always seen as somewhat of a dark art. Mm-hmm. So yeah, do you see that there could be applications for this? Because there's a lot of difficulties that around, like, for example, faulting and things like this, where you have discontinuities, or you have communication, but you don't know how good or how bad it is. Yeah. You have the dreaded non-neighboring connections where you have had some subsidence, etc. So how do you see these kind of techniques maybe being applied in that kind of area?
Yeah, so I totally see your point. So basically an advantage that we have here when basically doing regional to global scale seismology is that we don't have to deal with that, right? And that mesh building is, I would say, relatively simple. It's not simple to build those meshes, for sure not. But it is relatively simple because the Earth at regional or global scales is very spherically symmetric.
But still, it would have been. For me, it's difficult to picture how this would look like in actually adjusted to the Earth. In the example you showed, it's kind of logical if it's a homogeneous medium. But then, if you look at the variations in the Earth, do you have a picture of what it looks like in this?
So maybe the closest maybe the closest I get is this.
This one here. Yes. Yeah. Okay.
So many people don't quite believe it that it really works, because they argue, okay, but then you have different wavefronts and so on and so forth.
Yes, that would have been my.
But the point is that in a nearly spherically symmetric Earth, your wave field has nearly azimuthal symmetry. It is almost axisymmetric. And even so, maybe I can draw this here. So even a P wave field, which may look like this, people say, okay, does it still work? Yeah, it does, because still in this direction it varies very slowly.
Yeah.
And it breaks your brain a little bit. So, yeah, I did. And here it really works because it's a solution that's tailored towards a very specific problem. And building such wave field adapted meshes for smaller scales, your prior knowledge about the structure of the wave field may be much less easily captured mathematically certainly a lot more complicated.
Yeah.
So I'm pretty sure that this method acquires its efficiency from falling into a very narrow niche.
Okay.
Thanks. Okay, more questions, or do we continue with Lars and the next section?
Okay, then if not, then I would stop sharing and leave the floor to Lars.
All right, can you hear me?
Yep.
Yeah, let me get your faces on there too, so I can have a little bit of interaction.
Yeah.
So there's now, I think, a piece blocked of this thing. Oh, this looks better. All right, so I will be talking about reusing information during Monte Carlo sampling, using physics-informed neural nets. And this is similar in spirit to what the LBFGS auto-tuning is, but its actual implementation is quite a bit different. So I first want to tell you a little bit about the inspiration I got for this stuff and about the setting of using these artificial brains for Monte Carlo simulation. Sometimes in inversions, you don't have access to efficient gradient information. This was the case for Aleardi's study in 2020. The citation is given on the bottom if you want to look it up. But what he had was an inverse problem for which he couldn't compute gradients, but it was still high dimensional. So you, on one hand, you cannot really use Metropolis Hastings because this would be expensive. But there's no direct information you can supply to the Hamiltonian Monte Carlo algorithm. So what he did is he realized that you can still compute gradients based on finite differences. So in this plot on the right of some mock misfit function, he basically computes a forward simulation twice extra and uses a difference formula to compute the gradient at a single point. The idea behind this then is to do this a few times, throw a few of these points into model space, compute the gradient a few times, and train a neural net to distill this information and do some smart interpolations between all these points. Once you have a smart interpolator like this, you could give this neural network to a Hamiltonian Monte Carlo sampler and let that sample the actual target distribution. Now, the problem with this is, of course, finite differences become expensive at scale. So this doesn't scale well. There's, of course, other settings where your gradients are very expensive, and this is basically everything that was pre-built up to this. These large-scale simulations of wave fields in the Earth, they are still expensive. Even though we use the edgewing method, they still might run for half an hour, a few hours, or a few days. So the idea here is that a lot of the information during Monte Carlo sampling is actually wasted. There's a lot of redundancy. Our prior information is usually not used to generate new samples. We have burning part of our Markov chain that is discarded. Sometimes we actually mess up ourselves and we get the tuning settings a bit wrong, so we have to restart our chain. And as you can see here on the figure that Andreas showed us a while back, the Markov chain algorithm usually comes back to the same space, to the same place in model space. So it doubles back a few times. Additionally, in the HMC case, all these crosses are points where we computed our gradient that we used to propose a new sample, but we never stored this anyway. So all this information, the idea is to distill this into a neural net, to accelerate our exploration of our posterior by using this neural net. Specifically, what Aleardi did is you start at some point, you make a trajectory using our Hamiltonian physics, but instead of using the inverse problem to compute this trajectory, you replace this by a surrogate. And the surrogate will be your neural nets that I'll show in a bit. So these are typically much faster to evaluate than a wave field simulation. One thing he doesn't change is the final computation. So at the final stage of the algorithm, it still computes one wave field evaluation or one misfit evaluation. So that means that our true physics is still used to make the acceptance step. So the brains of this method is really neural networks. So I will try to give you a crash slide even into what a neural network does. And basically these things are so popular now that they're great tools for some stuff, but they're should really take the time to maybe to look this up. So what we'll look at is a basic fully connected net, which is shown here on the right. It has a series of nonlinear maps between the input and the output of the network. In this case, our input is a two-dimensional vector, and our output is a one-dimensional vector. It has 3 layers, and because it has 3 layers, it has two nonlinear maps between all the layers. So we have our input layer, our hidden layer, which we don't observe at all, and an output layer. To go from one layer to the next, we apply our nonlinear map, which you can see on this section here. Our input vector is multiplied by some matrix, W1. We add some bias, and then it is put into a nonlinear function. So this first part is a linear transformation, followed by a nonlinear one. The key component of this activation function is that we have its analytical derivative. This will be important later. So our hidden layers, it can be 1, it can be more. They also can have different dimensionality for the input. So this is a 4-node wide layer, and our network is 1 hidden layer deep. After this hidden layer, we apply similar nonlinear transformation, some weights, some bias, and some activation function. Now, the key of a neural network is to predict the correct outputs. And you can train a neural network by changing this matrix W and by changing this bias for every connection between layers. Additionally, there's, of course, a lot of arbitrary choices. Nobody says how many layers you need, how wide they have to be. The only thing that's consistent for one problem is your inputs and outputs. One other arbitrary choice is the activation function. This is a few typical ones, but what they all have in common is that you can take some analytical derivative of this thing in your code. So that means you can optimize it. Most of these things are implemented in popular software packages such as TensorFlow, PyTorch, SciPy. But what these things all have in common is that they use automatic differentiation, and they usually run on your GPUs. That means that these things are scalable really well in clusters, for example. And these derivatives are rather painless because the computer understands the operations that happen. So what Aleardi did in his paper to use a neural net for Monte Carlo sampling is the following. He had an amplitude versus offset data set, which he wanted to invert, but he couldn't compute gradients, obviously. So what he did is he used a finite difference stencil to compute a few points in model space, the exact gradient. His neural net then distilled these observations such that he could predict the gradient in between. His network architecture is schematically shown here. It has some amount of hidden layers with some amount of nonlinear transformations. Its input is our model vector. So this is just our Earth models put into a nice vector. And its output is a gradient for the misfit function towards all these model parameters separately. So for example, if the first node would be p-wave velocity of the Earth model, the first output node would have been the derivative of our misfit function towards p-wave velocity. And he used this net for Hamiltonian Monte Carlo sampling. And the conclusions from this was that this works really well. This sampling is a lot faster, all in all, so combined with the training, than computing the finite difference derivative during the Hamiltonian Monte Carlo algorithm. So that means there is some benefit in doing this. One problem with it, however, was that there were no maths involved in outputting these gradients. There's no analytical derivative and no requirements to these things. And lastly, this whole network was trained before starting sampling at all. So any information that was gained on the fly was not used in the network. So now what we thought about is equipping our brains with a sampling theory. And this is not how I started thinking about this, but this is what I figured out with someone at some point, that this is the equivalent of using a sampling theory. The problem with Aleardi's approach is that he's predicting n different components, so n different gradients in n dimensions. For every input dimension, we have to predict one gradient component. And there's no mathematical link between. So our modification is to only predict one function, the actual misfit function, and then somehow incorporate the analytical gradient in this thing. So this takes us from learning n functions, so all these different outputs on the right, to predicting just one and taking its derivative. So this can be approached from a very specific direction. If you look at gradients in the context of Fourier transforms, they are actually just a filtered representation of your original function. And this filtering means that we can apply the Populist sampling theory. This is basically an extension of Nyquist. Nyquist says with a given amount of samples at a given frequency, we can reconstruct our function to a given extent. Populist says if we additionally have filtered copies of our signal, we need much fewer observations. The thing is, however, most mainstream software doesn't allow it. TensorFlow, PyTorch, these are things that are kind of unknown to computer scientists. It doesn't make sense for them to work with the gradients of observations. So we had to re-implement this whole thing in some automatic differentiation network. And for this, we use checks. And if you're interested in these kind of things, I would really suggest looking it up. It actually also works for your simulation code. You can take gradients of simulation codes, but it's based on automatic differentiation. And this incorporation of the gradients of the misfit function is very similar to gradiometry in seismology. If you observe the wave field and its derivatives, you also learn a lot more. And the same is the case for the misfit function. Over the last year, I've seen it being applied at a few conferences in geophysics, and they always appear under the name physics-informed neural nets. And this name might not always be applicable, but it's based on that you use the adjoint method to obtain the gradients. And this adjoint method is usually derived with physics in mind. So what we propose is to use a network of the following kind. It still has this input of your inverse problem dimension, so your Earth models. It has some hidden layers, but the only output it has is the misfit itself. So this is really the misfit function. You have some observations of the misfit function, and your neural net tries to mimic that. But additionally, we take the analytical derivative of this node. So really, we go through the network and compute the derivative of this thing towards the very input. And we also output these. So the trick now is, if we observe the gradient, we can use this in the training of a neural net, really increasing the amount of information the net has to train. So now it's time to try these nets out with some test functions. And my favorite one in 2 dimensions is the Himmelblau function. It's a function that has multiple local minima, and it doesn't really look like a Gaussian. And to train our neural nets, I gave it some red crosses as observations. So at these points, the neural net knows the misfit function. We will train 2 nets, one which has the gradient information and one which doesn't have this gradient information. Now it's important to realize that this Himmelblau function is already fast to evaluate. It's analytical. So this is not really the case where we would see speed up, but we would see if our nets actually can approximate a function. The neural net is trained such that it minimized the root mean square error between the gradients it has seen and the gradients it predicts. And it uses a specific type of ADAM optimization, which is a specialized LBFGS thing that is used a lot in the machine learning literature. Now, the results of these 2 nets are visually quite striking. In the middle is a neural net which hasn't seen the gradient information. And on the right is a neural net that has seen this gradient information. And qualitatively, you can see these contours are much better represented in the case where this adjoint information is available. Now with this net, trained on this Himmelblau function, we can try to do some sampling. But our acceptance rate, and this is important, is still with the true physics, so with the true function. So we replace everything in our algorithm with the surrogate, except really determining if we go to a new model. This figure we've already seen. This was from Andreas. Here he showed the autocorrelation of samples in a chain. And this is the exact same thing that I will show now. So on the bottom left subfigure, you see the gradient sampling, the Monte Carlo sampling without the gradient information. And on the bottom right, you see the network sampling with the gradient information. And I'll be the first to say that the differences are not too stark. If you look at the autocorrelation functions, which are the top right of the subfigures, their decorrelation length, so the point where it first crosses to 0, are quite similar. There is some lower value for the network with the gradient, but it's not extreme. You can also look at the independence between 2 dimensions. This is cross autocorrelation, and this is a bit stronger with this network that hasn't seen gradients. But all in all, there's not a huge gain in using gradients, a little bit. But this is only 2 dimensions, and we expect this kind of thing to be exponentially more useful in higher dimensions. So scaling up is the next part of this. And for this, we look at a relatively highly nonlinear inverse problem. The case of elastic full waveform inversion. And elastic means that we have a shear wave velocity, a p wave velocity, and a density that we try to invert. Based on a finite difference simulation, but we do not invert directly on the grid. We use some Gaussian wavelets because this reduces our problem dimensionality. We have 192 free parameters. And for context, one solve takes about 1 second. Now, the trick really here will be to replace this 1 second solve by a much faster neural network approximation of the gradient. If we can do this efficiently, then our sampling will be sped up, hopefully useful. Yeah. So for the both networks, one that has seen the gradients and one that hasn't seen the gradient, we give it the same amount of training time, about 7 seconds on the GPU. This is really fast because we want to keep it much smaller than the Monte Carlo. But in these 7 seconds, the algorithm, the neural network that uses gradients has also seen the gradient information. This is not shown to the other network. We measure the performance in recall. So how well does the net remember the values that it has observed? If it repredicts a misfit at the correct level, so if it has seen a misfit of 500 at some point and it predicts the same misfit at the same point, then we say, okay, it's recalling pretty well. This is one measure of performance for neural nets. And we can see here that there is a striking difference between the standard net, which hasn't seen the gradient information, is predicting, for example, in this area, misfits of 800,000, where it should be around 400,000. On the other side, the physics-informed net is predicting most misfits accurately, the misfits that it has seen. So this is already interesting information. In the same time we gave to train these networks, the physics-informed net learned better to remember the misfits. What we haven't tested here is Aleardi's implementation, where he separately predicts all the gradient components. That is something that we will do at some point. Now, of course, the interesting thing is to use these neural nets to sample this posterior distribution. So again, for the Metropolis Hastings acceptance rule, we use the true physics. So for every sample, we at least simulate the wave field once. We, however, found that both the Markov chains have extremely slow convergence. They have minimal movement in model space. That means every subsequent model moves only a tiny fraction compared to the previous model. So what you see here on the right is the step size of the Hamiltonian Monte Carlo algorithm. The step size controls how much we accept. So how big are our deviations from the previous model. And you can see that this goes to pretty low numbers. So 10 to the minus third, 10 to the minus fifth step size in the HMC algorithm. So we're moving very small distances from our previous model. This in turn means that our autocorrelation is extremely high. Compared to the step size of our true physics, so the one which uses a wavefield simulation, this is a big difference. So this is, when we use the true physics, we can get away with a step size of 0.1. That means that even though we've sped up the gradient computation, we in turn now move very slowly through model space, about 3 orders of magnitude slower. So if this is to work, our neural net at this point needs to be 3 orders of magnitude faster than our physics. This is not the case for the one I implemented. And the problem here is gradient recall. How well does the neural net remember gradients that it has seen? And in both cases, the one trained without on the left, and the one trained with the gradient on the right, it doesn't remember the gradient. These things seem almost randomly distributed. You see here for a gradient as observed at 500, it predicts anywhere between -20 to 20, but nowhere near this number 500. So the gradients that the neural network predicts are not doing well. They are not accurate. And this leads to improper Hamiltonian Monte Carlo trajectories. One reason for this is that we used root mean square error. You can see here that the gradients are about magnitudes or about 1000 to anywhere to 10. But if we look at the misfits that were observed, these are much bigger. So there is a thing going on. We have 2 types of information that are both important. So these are 2 objectives and they both need to be minimized. So there is some unknown weighting between the 2 that will probably optimize this. So there's a few unanswered questions for us. And this boils down to, here this measure performance, that's what I just talked about. Sorry, I want to stop. But one question is, of course, what's the best network type? And now I looked only at the neural networks, but another example could be to use a Gaussian mixture, which already assumes that our posterior is some combination of Gaussians. These things have been shown to approximate posterior distributions really well. As in any neural network or any machine learning application, what is the best architecture? How many layers do you need? How wide do they need to be? What is the optimal activation function? That's a lot of investigation that this needs. How to measure performance? So we used root mean square error in this case, but maybe we could do something with the angle of the gradients or the magnitudes that would improve this. Maybe we wouldn't need to use or surrogate at every point in the Hamiltonian Monte Carlo algorithm. Maybe there is some benefit in evaluating true physics a bit more. And because we're altering our proposal function, we also technically have to alter acceptance criteria, which we haven't done at the moment. Some final words, and I have a different conclusion than Andreas has usually. But we've seen that the analytical derivative information is very useful, both in the 2-dimensional case and in the high-dimensional case. Our representation of the misfit function increases drastically. This thing is very cheap to train on the fly, so you could run this during your Monte Carlo algorithm, and it would not impact performance significantly. It's basically a side product of doing MCMC. And one application that I can see it used for is on-the-fly subsampling. So you condense this huge amount of samples that you generate in high dimensions to something easily represented by a neural net, which is fast to evaluate. So if you have any questions about this, feel free to write me or Andreas, and I'll be happy to take any questions now.
No, that's something for Ryan. Thanks, Lars. Thanks a lot. Ryan directly has a question.
Hello. Yeah. Hello. Yeah. Thanks for your presentation. So I have 2 questions here. So first of all, I just want to know what is your exactly your inputs, because I'm quite confused following the whole presentation. So kind of what is exactly the input of your neural network? That's my first question. And then my second question, how do you train this one, and how do you ensure that your training set can give you really good interpolation really good prediction when you put this neural network into the stream of the MCMC.
Right. So yeah, I should have been maybe a bit more clear. This input of the neural network is an Earth model. So it's our model space, a pointed model space. So it's basically a model vector or the position of our spaceship at one point. As for ensuring, the second question was ensuring how well it actually represents the misfit function.
Yes, how do you pick the best training set so that later when you put this neural network in your MCMC, it will not give you additional error because of misprediction of the neural network and the real misfit function?
Yeah, so this is of course a great question, because if you already train your neural network on completely the wrong region of model space, you're basically giving it a very strong bias to go in that direction. One thing that ensures that you don't completely go wrong is that there's still the true physics at every acceptance step. So at the end of one trajectory, you still use the true physics to see, should I go there or not? Basically reduced your amount of physics evaluations, but it's still in there. And another thing is you could use prior chains, so stuff that you have run before to train this, where you already know is the misfit high or low, and you use only the lower misfits to really capture information, because those are the interesting ones.
So
yeah, is it right?
Sorry, follow-up question. So somehow it means that you somehow train it online together with side by side with the MCMC.
Yeah, that's one thing that you can do, and then you can assign weight to every observation by the value of the misfit.
Okay, so do you see any problem with the growing training set? Because for example, now you see the let's say the basically the lowest side and the highest side of your value, and then suddenly maybe the range can change a bit, and then will you do the augmentation to the training set, or?
That's also a very good question. So much like the auto tuning that Andreas has shown, it would be, I think, wise to have a rolling buffer. So you store the last n samples. But in addition to the LBFGS, this neural network has some memory in it. The parameters from previous iterations are still used in the next ones. So it might be a more hybrid way of storing information over a longer time. You kick out the oldest samples, you get in some new, but in the network is already the history of what it has seen.
Okay.
George?
Thanks for talk. So for the output of the neural net, I assume you have this posterior probability, or the negative log posterior. And then you calculate the gradient that's respect to the input parameter, right? And
yes.
Did you take L2 norm of both this posterior and the gradient as a loose function?
That is currently our implementation. So we have the L2 norm on this observation and the L2 norm on these.
Yeah.
What we've experimented with is also using the angle of the observed gradient and the predicted gradient. So this might avoid some of these problems where you have magnitudes that oppose each other. You basically want it to point in the right direction. That might be more important than the components themselves.
Okay, thanks. And what's the highest dimension you have tested these methods? And how many training samples you use?
So I've done a test function very similar to Andreas's 1D full waveform inversion with about 500 free parameters. And I try to give it a big training set, so about 5,000 observations. But still, that was using the L2 misfit on the network, and it wasn't training too well. It gave some discrepancies. In some regions it worked, and in some regions it didn't.
Thank you.
So I still myself have a lot of open questions about where exactly the region is where this is feasible.
A lot of interest in these topics. Is more questions at the moment, or we leave it for the end for some final discussion. Then we hand back to Andreas, I think.
Shall I stop sharing, Andreas?
Yeah, if you stop sharing, then I start. Okay, can you see this?
Yeah.
Yeah. Okay. Good. So a few slides to wrap up, maybe leaving a few minutes for final discussion. So it's really just an outlook, and so you've seen a whole bunch of approaches, and they work individually very well. But of course, the goal in the end is to put them together in order to get a 3D probabilistic full waveform inversion to run. So basically, I wanted to show you where we are standing and what the long-term goal is, and what I think of, maybe a little bit optimistically, what might be achievable. It's never bad to dream. So the long-term goal is to, as I said, really run a 3D probabilistic full waveform inversion based on a combination of different methods, and methods that I think are quite essential and useful are indeed this Hamiltonian Monte Carlo, the auto-tuning based on quasi-Newton methods, which is particularly important when you're looking at model parameters that have vastly different sensitivity. The wavefield adapted meshes, or some variant of it, some more clever forward modeling than we're doing traditionally, and hopefully also the physics-informed neural networks. So obviously we're not there yet, but I hope that I can convince you that it's actually at least moving in the right direction. I want to show you a little example that Lars actually produced. It's going in the direction of a real data inversion at a global scale. Where we are using globally recorded earthquakes as sources, and one of them is shown here. It's in Northern Africa, and has been recorded at more than 2,000 locations on Earth, where we have 3 component recordings. And at the moment, we are looking at very long periods, so at about 150 seconds. And there, a single simulation takes about 20 GPU minutes. So that actually means that you could run a global scale simulation at 150 seconds, essentially on your laptop in 20 minutes. And so I think actually, if we take into account that we have already now supercomputers where we may use 1,000 GPUs, then I think actually with computational budgets that as even as scientists in academia we can get with relative ease, I think it is actually realistic already now to maybe draw a few million samples. Okay, so maybe this is not enough to answer real questions, but I think it already illustrates that even today we may be able to do something. And so I'm actually reasonably optimistic that in maybe a decade from now, this is something that we can run, maybe not standard, but in a mode that actually starts answering scientific questions, and hopefully within last PhD thesis, get something to run that actually at least demonstrates that it's doable. And I think that would already be an immense step. There's still a couple of challenges ahead. Interestingly, I think most of the technical ones may be actually resolved. The ones that remain, I would say, are more conceptual and maybe also more scientific. So what are actually clever parameterizations of 3D heterogeneity in the Earth? And that is, it's really not a mathematical question. It will depend a lot on what we actually want to find out. And what are useful lower dimensional quantities that we should actually extract? So it goes back to a discussion that we had a little bit before. So in principle, we have methods to sample those high dimensional posterior distributions. What do we do with them? Right, so we can quantify uncertainty as much as we want. We are flooding in information. But how do we condense this in a way that it becomes useful, for example, for a geologist who may not know what Hamiltonian Monte Carlo is? And so how do we condense this in a useful way? And also this very likely will be application specific. And of course, also what are actual scientific problems that we may want to address, in addition to just plain quantification of uncertainties. And I'm pretty sure that if we if we formulate scientific problems very carefully, then we may actually further increase the efficiency of those methods very substantially. A careful formulation of scientific problems can go hand in hand very efficiently with dimensionality reduction, for example. So before I finish up, some resources that I would like to mention. There's a whole bunch of publications. I think the one of the most comprehensive ones, and I would say most readable ones, is actually this Hamiltonian Monte Carlo solution of tomographic inverse problems, which gives all the background on Hamiltonian Monte Carlo in, I think, a relatively accessible way, without excessive mathematics and really basic math, but also the Hamiltonian null space shuttles. The Bayesian elastic full waveform inversion that I have shown in 2D is contained in this paper, which came out of Lars' master thesis. The auto-tuning that I talked about is not yet published, but the revisions that we got from Geophysical Journal International were extremely harmless, to say the least. So we hope that this will be published very soon. The paper is about 40 pages long, so my suspicion is that the reviewers just wiped it off their desk and said, we don't want to see it anymore. So the wavefield adapted measures or the waveform inversion based on them is contained in this paper by Sir Vitrastoson, who's one of my PhD students. Okay, we have a few other resources. I would like to mention our YouTube channel, which contains a bunch of educational movies about most of the basic concepts that I have introduced here, like the wavefield adapted measures or the Hamiltonian Monte Carlo sampling, so on and so forth. We have a software library that you can find on our website. So it's a whole collection of research and of educational and also of production code. So when you go to our website, swp.ethz.ch, there's a software button where you can find a whole collection. And also Lars and Andreas Fichtner, a postdoc of ours, they're developing a very dedicated HMC tomography package. It is not yet published, but you can get access to it by just dropping an email to Lars, and he will be happy to share this. There will also be a paper about this appearing hopefully pretty soon. So with this, I would like to thank you for your attention, and I would be happy to answer more questions. Thanks a lot.
Thanks a lot, Andreas and Lars, for this very nice introduction to the topic and going still very deep into the current state and what is happening right now. Really fascinating to see where it's been going the last couple of years. And this outlook to the future is exciting, I have to say.
Thanks. Yeah,
so,
hopefully.
We still have time for questions, though, from the audience, maybe now from this entire big topic we've been looking at. And also for, if that's fine, Andreas. I mean, we had questions before already in our break, if we don't want to take too much from you.
Yeah, no, that's totally fine. Yeah.
I have one quick question. Maybe that's a follow-up from Tristan's question before a bit. So when you now say that at the moment you're using these 1,000 earthquakes and to calibrate or to perform the inverse problem, and now you said also that basically one run would be approximately 20 minutes GPU time, but that on big clusters it could be parallelized. So how would you actually? So that's what I understood. Is that right? So you would parallelize it for the separate events separately and then combine the results somehow?
I think you would combine on both levels. So you would combine. You would parallelize the simulations themselves.
Mm-hmm. Okay.
But you would also run simulations in parallel.
Mm-hmm. So you would do both. And our experience is that you have to tweak this a little bit depending on the queuing system on your supercomputer. Mm-hmm.
So some supercomputers give preferences to big chunks.
Yeah.
Others to small chunks. You usually experiment a little bit with them.
But all at the moment give big preference to GPU computing. So I think you're well positioned there. That's also what we see in Jülich. I mean, this is always the discussion we have.
Yeah. They're obsessed by this. Not sure it's really an advantage, but
I mean, now it's getting harder to get GPUs now. Everybody's, you know, mining Bitcoin. So maybe we go back to CPU clusters at some stage. Okay, more questions. Open to, of course, everyone. Denise, to the physics-based neural networks.
Yeah, of course, there was numerous ones.
Or to how to get these reviewers who are favorable.
Yeah, I mean, that's more general question that's independent of what method you use in the end. But that's a different point. But maybe, did you experiment maybe a bit more with using different physical constraints also to ensure that the surrogate model is actually preserving most of the physical structures?
Lars, I think this is for you.
Yeah, the physical structures, what exactly do you mean with that? The physical structures in the misfit function?
I mean, it depends a bit on what you use as an input, but I assume you use as an input something that's coming from the wave equation in a broader sense. So you could generate surrogate models that preserve the properties of the wave equation.
Yeah, so these surrogate models are really, really free in that sense. There's of course a whole branch of surrogate models that make assumptions and simplify the physics. But when you're training a neural net, it's basically random parameters with random functions together, and anything can come out. So there's no real restriction in this sense. I thought about using these Gaussian mixtures because they are always, they decay towards infinity, and in that sense, they look like misfit functions, right? Like probability densities.
Yeah, what I was aiming at a bit is the approaches that George Kaniadakis is using. They call it also physics-informed neural networks. That's where maybe the confusion might come from as well. And they are using the PDE itself in the loss function to constrain the model.
So
they're using automatic differentiation to get the derivatives that you need in the PDE.
Yeah. So I am still using the PDEs, but it is to obtain the observations of the gradient. So before I start anything training-wise, I make some samples in model space, and I compute the gradients at those points with the PDEs. And that's
sorry. But then you're limited to the observation space, right? So you would get troubles if you have, let's say, something that's outside of your current observation space. Let's say if you get a new seismometer somewhere outside.
It's not really observation space, but you're very right. So if you don't throw in some region of model space that turns out to be interesting, you're in trouble. But the whole field of machine learning is in trouble in those cases.
Yeah, that's yeah. So in this case, also when you say when you would use a Gaussian mixture model, you would actually directly apply this on the posterior. So for the posterior space. And then the question is always with Gaussian mixture models, we also had tried this in a couple of studies, that it's very difficult to actually generate a new sample. Did you look into this already?
Generating samples from Gaussian mixtures?
No, not from Gaussian mixtures, but to create a new covariance function, which is giving you actually a new mixture to adjust the mixture distribution itself. It's actually trivial.
Yeah. The training is actually kind of unstable. And there are some issues there. Yeah, I've experienced these.
But they're okay.
I'm not sure how to fix this, but there's some stuff out there.
There was a publication 2 or 3 years ago which was quite promising. We are using this in one of our methods, but it's still can still be unstable a bit. Okay. I also have one more question to Andreas for the. We now go maybe back to this what Tristan asked as well. If you look at reservoir scale, just for us to see a bit the. So what is the state at the moment in this field when you go to smaller like reservoir scales for full waveform inversion? Can you say something about that? Is this something where the similar methods are applied right now?
I would say no. Well, I mean, there were Hamiltonian Monte Carlo solutions, Hamiltonian Monte Carlo full waveform inversions at reservoir scale. So there was one by Mrinal Sen and one of his former PhD students. So that I think appeared two and a half years ago. But the wavelet adapted measures I have not seen. Also the auto tuning I have not seen.
Yeah,
the wave field adapted methods may be a lot more difficult there.
Yeah.
So it may not be made for that. And the auto tuning, I think, is still something that is known really in the statistical computing community, but not very much outside. So just this Hamiltonian Monte Carlo itself probably takes some time before it leaks into geophysics.
I mean, we've been using it for the geologic modeling parts, but of course a lot smaller parameter spaces in our case, because we look at the parameterizations. But I mean, it is really promising also because we have kind of strange posterior spaces, but not as high dimensional. So we have a trade-off a bit there.
Yeah, okay.
But that's really interesting. Tristan?
Yeah, it's me again. Just to kind of like piggyback off what you were saying just now with the reservoir side of things. I imagine that the sort of uncertainty about the measurements that you have is relatively low for the cases that you're looking at with the sensors seeing the seismic activities and the waves coming in.
Yeah, I think the uncertain. So we have the luxury. So at least in global seismology, we have the luxury of swimming in data and of picking those data for an inversion where the quality is very high.
Yeah.
So so having signal to noise ratios of 100 is not unusual.
Okay. Yeah, because that's something that's, particularly when you come to reservoirs and wanting to do like history simulation of those, that's always a very, very big challenge because there's so much uncertainty just around how much have you actually produced from your reservoir, like never mind the makeup of the reservoir itself.
Okay, but also I thought the amount that you produce, that should be easy to quantify. You just count your barrels. So is it not as easy?
Well, yes and no. So like if the volume measurements of the oil and gas at surface, they actually depend on the separator trains that you use. Okay. And so, for example, if you have a single and multi-stage separator, you don't necessarily get the same volumes because of, well, the entropy associated with the flashes.
Yeah.
So in a lot of cases, that's not being metered very well, or the makeup of the fluids themselves are not understood very well.
Yeah.
So there you have a lot of uncertainty involved with the entire process. So actually, doing history matter is not just a matter of what are my reservoir properties, but also what's the uncertainty about the history itself. So it's almost like you would have to put the inputs into this Hamiltonian space shuttle itself.
This is actually, it can work to your advantage because uncertainty quantification actually becomes easier when your observational uncertainties are larger. So basically what tends to happen is when your observational errors are very small, then your posterior distribution tends to have very sharp valleys and very thin valleys. And everything and the topology of your posterior becomes a lot more smooth and a lot wider and more gentle when your observational uncertainties are larger. So actually then your posterior becomes more easy to sample. So paradoxically, if your uncertainties are large, then exploring the distribution is actually simpler.
Yeah. Okay.
Ryan, last question maybe.
Maybe okay. And then this is kind of like a very general questions, more about the Bayesian, the Markov chain Monte Carlo, because since the first time I read like papers related to the Bayesian Markov chain Monte Carlo, there has been like several basically focus, let's say, on the prior side. Let's say, did they try multiple priors, how to deal with multimodals, how to deal with non-informative priors, Gaussian and etc. And then there has been like a focus more on the posterior sampling, like what you are doing here, and then like they are developing like stochastic Langevin and all those stuff, all the sampling, the multiple way of sampling method, and then like the algorithm itself. Like, what do you think? Like I don't know, like somehow the most impactful. What I mean, like something that can basically change like how this can be applicable for like the real world thing.
So I think what is really missing, maybe Lars can answer that question as well. My take on this is that one thing where we still need to make progress is actually something much more simple. And that is a proper quantification of the observational uncertainties.
Mm-hmm.
And so the thing is, all the uncertainties in your model parameters that you infer, they depend very critically on your uncertainties in the observations. So if you pick travel times, as people still do a lot, then you can do statistics on your travel time picks. You can do this Monday morning and Friday afternoon, and you can look at the difference. If you do full waveform inversion, this becomes a lot less trivial. And coming up with a method of quantifying those uncertainties, coming up with basically a prior probability density in data space in a more or less automatic fashion that is practical, that is not totally academic and nobody looks at, but that people actually use. I think that would be enormously important and very much appreciated by many people.
Mm-hmm.
It can't be so difficult, but usually nobody's really touching it.
Thanks a lot. I think that's a good conclusion. All right, we have a quick, no, it's 1/2 I think we release Lars and Andreas. Thanks a lot for, that was really a fantastic overview and an insight to this topic. Jan put it very nicely in the chat. He has to leave already, but it was really interesting and understandable even without deep prior knowledge. So
thanks a lot.
We hope that there's an adjustment in the posterior knowledge here. Definitely, we're sure about that. Thanks a lot for, sorry?
Yeah, also thanks a lot. We hope we could do something for your biological neural network.
Yes, exactly. There's certainly an adjustment there.
And contribute something to the training. And again, thanks a lot for the invitation. It was really, really a pleasure.
Thanks so much for coming. And let's hope that we meet again sometime in the future again.
I hope so as well.
All the best and all the best, Lars, for the PhD.
Yeah, thanks.
See you.
Bye. Stuff works.
Thanks for the presentation.
Good evening. Ciao.
Have a nice evening.
Bye.
Bye.
Florian,
yeah.
Will the presentation be shared afterwards?
It's recorded.